Okay, everyone sit down. You can tell your story about your dog later. Yeah, this is the start of my routine. Welcome.
She'll be here all week.
I have been here all week. Okay, this morning we're going to change gears a little bit. We're going to dig into the science part of the ASO workshop. I'm excited about this morning, being a scientist myself. So first up, we have Adrian Harpold for the University of Nevada, Reno. He's been working with the data a bunch. We've known Adrian for a really long time. He's been speaking at these workshops every year, and it's always really fun. So he's going to be talking about hydrological modeling and long-term water planning.
Thank you, Kat. I will be as fun as one can be at 9 a.m. But thank you for being here. It is like my fifth or sixth one of these. I gave a very sort of open-ended generic title, but I always like to be a little bit provocative with the talks here. It's something about the space that is here. And so I am bringing a little provocation in. I'm bringing in some ideas that I've been thinking about, but you guys are going to be some of the first to see these slides. I want to talk about the future of mountain snowpack and how are we going to predict our future snowpack water resources. And I am going to spend quite a bit of time just thinking about sort of that philosophically, but I'm going to then point us towards some challenges that are these, what I'm calling the four horsemen of predicting and modeling and measuring future snowpack. And then because of the crowd, we will put this into the context of Lidar and airborne Lidar. I won't. I talk about Albedo. So snowpack modeling, snowmelt modeling, I'm going to probably use a bunch of terms interchangeably like that, and snow measurements are this really kind of interesting conundrum of we have pretty good tools that work pretty well. A lot of them have worked pretty well for a long time as a product now of University of Nevada, Reno, right? Like the church sampler is like 100+ years old. Degree day models work well. We know that solar radiation is the driver of snowmelt. We don't even need to measure that in some ways, right? We can predict that super reliably. We can see the snow. We can sense a lot of things about the snow surface. And we now have this like reliable LiDAR technology. But at the same time, we have these sort of interesting conundrum that we still don't really have models that we all accept or think work particularly well. We have real issues with precipitation that I'll talk some more about. The snowpack energy budget is very complicated. If you haven't spent time thinking about it, take my word for it, very complicated. Similarly, snow is this really complex thing, right? Where it sublimates, it evaporates, it melts. It's a porous media. So when the water drains through it, it has these properties. That is also very complicated. So we are kind of juggling the simplicity and complexity. And I think as a scientist, I am sort of thinking about this. But this isn't all fun and games, right? Like we are working on an issue that is important for our society, namely water resources. And we are coming into a century where we're sort of flipping our snowpack. So if you think about this graph of the amount of snow in the Sierras from this review paper, we're going from a snow-dominated system to a no snow-dominated system. And that's scary, super scary for everybody. Hard to think of many upsides from this, at least in the Sierras. But did I say everything I wanted to say? But what we need to recognize is that those graphs are embedding a whole bunch of science and a whole bunch of uncertainty. And that uncertainty arises from a variety of factors. So this is from the same paper. They're showing some uncertainty related to the Western US. They have a bar for California as well. And they're showing uncertainty. I'm not going to get into the details of it, but they're collapsing the uncertainty around climate scenarios, around the GCMs themselves, how they're downscaled. So the snowmelt model is somewhere in that, but there's all this other uncertainty. I'm going to try to bring it back to the snowmelt model, but know that when we're looking out in the future, we're collapsing a lot of sources of uncertainty. One of the challenges is, how do we reduce uncertainty? How do we pick more predictive models for the future? We can't benchmark our models in the future. We don't have data from the future, right? But we do have data from the past. So I think one of the challenges in snow melt modeling is, how do we benchmark our models and say we have good models, better models? We use SWE to do this mainly, but we're really challenged. Again, we don't have good precipitation measurements. We don't really have good SWE measurements. The thing we're really measuring very well at the moment is snow depth. So how do we validate models? When we take our Earth systems models and we pull them from a single location, we get ensembles of model predictions that look like that, which is concerning. This is the classic snow model intercomparison project. There's the second one they did in the forest. So even if we take all the models and we constrain it with the same precipitation, so we're using the same precipitation, we still see this big ensemble of models based on uncertainty in the models. And I'm not going to get too much into that uncertainty in the models, but we can talk more about that. So I think this leaves us at like a interesting paradigm where we know that we have sort of better models in one hand, but they're not really being used operationally. So that is it's hard to even explain why that is, but it has to do with model complexity, the complexity of applying these things in an operational thing. Gus is going to give a talk. There'll be talks about this later, but my argument provocatively is that if they were that much better, they would be being used operationally. One of the reasons that is because we have a very hard time benchmarking models. And I would argue, if you can't benchmark models, how can you say a model is better? How do you even have a pipeline to adopt new models? And then, the paradigm is that all of this is happening in a trajectory of snow change, right? Dramatic snow change that we basically know is coming no matter what. So I've been thinking about that paradigm, but then it's like, how does science, my job as a scientist, how do we sort of bring science to bear on this challenge? And I've tried to distill this down into what I'm calling these 4 horsemen, 4 challenges, and I'll try to go through this. I'm going to go high level. This is only a 15-minute talk. I pulled this paper and read it yesterday. It just came out though, so I do have that excuse. This is Mark Raleigh, Eric Small, ASO data. I think it's all ASO data, some version of ASO data over the years. They do it in the Colorado, they do it in the Sierras. It's a tremendous amount of data that they pull. This is like the classic thing. I'm not gonna, well, here, I'll use the pointer. In the middle is the Spratt Creek snow tell. You're getting one number continuously through time for snow water equivalent. Then you got elevation, you got vegetation. This probability distribution is showing the 50-meter data versus the snow tell at different scales. And I'm not going to show you that, but this is the classic conundrum, right? Of like, we have this network of stations. So in the Sierras, it looks like this, the dots being the stations. How do we get more information? LiDAR is obviously an amazing way to do that, but then how do we wring more information out of LiDAR to get at things like precipitation and snowpack? Well, in this paper, they're showing that more information is sort of happening in the middle of the season. Early in the season, it looks more like the snowtail. Late in the season, it looks more like the snowtail. In the middle of the season, it looks different than the snowtail, presumably because there's more information there. We have other challenges with precipitation besides just the amount and distribution. The phase of precipitation, especially in a warming world. Also the metamorphism of precipitation, or snowpack metamorphism and rain on snow events. So this figure is from a paper by Lisa Katz that's in the Journal of Hydrometeorology from a site that's like very close by, Sage-Hen Creek. We get big rain on snow events here. That's this historical cause of flooding. The variability, I'm sorry, it's a little bit difficult to see, but these are precipitation events along this axis that are ordered smallest on the left, largest on the right. The variability that you see in the bottom panel is an expression of the antecedent conditions controlling this TWI, the amount of water draining out of the snowpack, the water input. So it's the short story here is that the snowpack, the distribution of snowpack controls its response to rain on snow events through cold content. The second real challenge that we face that I do think there's a room for LiDAR, I'm still kind of wrapping my head around how to bring LiDAR to bear on this one, but latent heat is a real challenge with snowpack modeling, snow measurements. The snowpack sublimates. It also can evaporate off the surface. It's also melting. So latent heat can actually be both positive and negative. It can change through the course of a season or through the day. We did this very coarse study, Paul Brooks and I, that is showing one of the main drivers of winter snowmelt. So the snowmelt that occurs before April 1st, sort of peaks time periods, is very controlled by humidity. And this makes sense. Higher humidity, you get a bigger vapor pressure gradient into the snowpack, more latent heat or less latent cooling of the snowpack. We don't measure humidity. We don't really measure wind. We certainly don't measure turbulence in complex terrain. Our models do a very big simplifications of that, and they may or may not work pretty well. We also just know that our coarser land surface models are just sort of challenged to get these predictions correct at the handful of sites that we do have measurements from. Third of the horsemen is the radiative paradox. We have lots of challenges with radiation. We have snowpack albedo, we have landscape albedo. When a fire rips through, it changes the snowpack albedo and the landscape albedo. I'll show a little bit on that. But this example here is the shortwave, longwave trade-off from vegetation canopy, where when you're in a warm canopy on the top, snow disappears earlier under the canopy because the canopy is warm, it emits long wave radiation. When you're in a cold environment, the snow disappears first in the open because solar radiation is the major driver of ablation. So we took ASO data primarily, some other data sets. We were able to show these relationships across different climates, different topographies, and make some sort of inferences about how this works at a larger scale. All right, the last point I'll make is about fine scale heterogeneity. I think this is the easiest one to wrap your mind around how LiDAR comes to bear. Here's an example from wind redistribution in the Wind River range of Wyoming. This is an ASO flight flown over the Wind River range. The red dots that are hard to see through there are the perennial glaciers and snowfields. Eli Boardman will talk, I think, about this later this afternoon. But the point here is that by mapping these snow fields across elevations with LiDAR, he's able to show sort of counterintuitively that the lower elevation snow fields are ablating less. And that has to do with wind redistributions and making those snow fields more persistent. This is the sort of classic slide that I've shown for years and years and years, probably like every ASO workshop, but snow forest interactions are a great place to do LiDAR work. If you don't believe me, read my papers. There's a lot of opportunities doing snow vegetation work with LiDAR. I think the real challenge at hand is vegetation disturbance. I don't think we're bringing LiDAR to bear on vegetation disturbance in a way that we could. ASO is flying the Feather River. I believe flew it before and after some of these large fires, but we don't really have good tools to squeeze all the information out of those LiDAR data sets. We're in a period of really bad fires. I lived through the Dixie Fire. It was tremendously awful. Okay, here's my closing slide. How do we bring LiDAR to bear on this? We need to target accumulation processes. Precipitation is so hard to measure, right? Processes in the canopy. We need to target ablation processes. If we had this more paired with field measurements, especially like energy balance, we could do a lot more with the data sets. There's like a handful of places in the whole world that measure the energy balance of the snowpack. Targeting rain on snow events, I think, is potentially a unique thing that LiDAR could do. And then disturbance events. There's a lot of opportunity there. I think a lot about this. If anybody wants to think about vegetation disturbance and LiDAR, let me know. There's challenges. So with that, I appreciate your attention through that busy talk.
Thanks, Adrian. I think we have time for one question. If anyone has anything burning. Tom.
All right, I have a question for you, or kind of a comment. So you said that if the physical models and the spatially explicit models were performing well, we would already be adopting them operationally.
They were performing better than the current models.
Right. So I think, as Pat Hayes loves to say, inertia is the most powerful force in the universe, and in particular with respect to adoption of new technologies. And so I think part of that is caution on the part of the water managers and the forecasters. And so I think as they are continuing to improve, it's going to take time, and they'll sit side by side.
I don't disagree. I would sort of, I mean, I think
I say that based on experience. Go ahead.
I'm really covering my bases here, right? Real and perceived risk. So I completely agree. I think if they were substantially better, right? I mean, it's a risk reward. So I don't disagree, but my whole argument here is that they can be better. They need to be better. Yeah.
Because of the reach of everything else they can do.
And because we're going into a century of change where we're going to be the ones that have to predict what happens.
Okay, great. Thanks, Adrian.
Follow me, talk to me afterwards.
Yes, absolutely. All right, next up we have Michelle Hu. She just finished up her PhD at the University of Washington and is now with Mackenzie Skiles, another friend of ASO at the University of Utah.
Good morning, everyone. Thanks for the introduction, Kat, and thanks for the thought-provoking talk, Adrian, wherever you are in the room. My name is Michelle Hu. I am postdoc with Mackenzie Skiles at the University of Utah, 6 months old, and working with the Snow Hydro Lab. Today, I'm going to be presenting some of my work with my colleagues Alvaro Robertson, Yijing Liu, Joe Meyer, and Mackenzie Skiles about this very verbose title, Informing Process-Based Modeling with Satellite Remote Sensing and Assessing Improvements Against both in situ and ASO observations. All right, so we're going to talk about the Upper Colorado River Basin. We had a slew of great talks yesterday about this region, so we know that it's an important source of water to over 40 million people and more than 29 federally recognized tribes. The headwater basins are snow dominant in the UCRB and supply between 85 to 95% of annual runoff to the dynamic Colorado River system. So we know that this system is changing, and we're not the only ones. To meet these changing hydrologic systems, NOAA kickstarted an initiative about 8 years ago to promote resilience to water risks in the form of the National Water Model. The National Water Model is a hydrological modeling framework which provides CONUS scale forecast guidance to, at this point, over 3 million miles of rivers and streams, as well as in areas that previously did not have water predictions. But as Mike Anderson mentioned on Tuesday, I think, there are limits to what one single standardized model across the country limits to what it can do. So the interagency NextGen effort attempts to address these limitations by encouraging regional tailoring of hydrologic water resources models. In support of this effort, we're working on USBR and NextGen projects along with Cairo to partner with the Colorado Basin River Forecasting Center to develop a supplementary modeling approach to their operational temperature index SNO 17 model in the UCRB. They're going to be just all of the acronyms you can imagine in this talk. So that supplementary modeling approach is using the iSnowBal model. It's a process-based model. It simulates the snowpack mass and energy balance using meteorological inputs to drive the model. And this flow of mass and energy changes are explicitly represented with mathematical equations, which are then tracked through time. Oops. iSnowBal is spatially distributed, which means that these equations get applied to each grid cell over the entire watershed. And the energy balance of the snowpack then determines melt based as a cumulative result of these physical processes represented in that model. So our goal here is to mature iSnowBal for operational use in the UCRB for the CBRFC. I told you. So as part of this endeavor, our group is looking to improve modeled snow mass and snow melt errors, which have been attributed, thank you for the setup, Adrian, to precipitation inputs, net radiation, and snow albedo representation errors. My colleague, Yijing Liu, who is here today, is working to develop a canopy interception model to update precipitation inputs. Alvaro Ledano is using geostationary remotely sensed cloud cover products to correct incoming long wave and short wave radiation. And I'm going to be talking a bit about our work, our very preliminary results, working to improve albedo representation using satellite remote sensing MODIS albedo products in order to refine net solar radiation. Because net solar radiation is one of the largest contributors to melt energy, and albedo is a primary control on net solar radiation. So the version of iSnowBal that I'll be talking about today is called the HER-MODIS implementation. HER stands for the High Resolution Rapid Refresh Numerical Weather Prediction Outputs, which we use to drive the model. I've practiced this talk. MODIS is for the MODIS satellite remote sensing products that we are using to refine net solar radiation. And I want to acknowledge my colleague, Joe Meyer. This is based off of his dissertation work. Without all of his coding knowledge, setting up HER-MODIS, none of this would be possible. And he has tested this so far in the East River watershed in Colorado. Okay, so most snowmelt models represent albedo with time decay or date decay, age decay curves. This is because it's computationally efficient. But the way this works is that it's all based on new snowfall events. There's a predetermined set albedo maximum that you reset to after a new snowfall event that non-linearly decays until the next snowfall event. The problem with this is that we know these decay curves do not represent how variable albedo is over space and time. So instead of these curves, we're using those daily satellite remote sensing products to update albedo representation. Our motivation here is to contextualize this new implementation against an operational national water model, despite its limitations. The table on the left shows some of the key differences between these two modeling approaches. HERMODIS is very developmental in the UCRB. National Water Model has been operational for years and is nationwide. There's also a difference in terms of spatial resolution. We're running the HERMODIS ice snowmelt model at 100 meters, and the National Water Model is output at 1 kilometer resolution. So our objectives for this work are to establish baseline performance, benchmarking, if you will, current HERMODIS implementation across these snow-dominant headwater basins in the UCRB. We're going to evaluate snow mass and melt representation using comparison data sets, SnowTel sites, ASO snow depth, as well as against the National Water Model. And throughout this, we are trying to figure out we're trying to assess feasibility and identify barriers we might encounter when running HERMODIS at large scales, again, in support of these operationalization efforts. All right, so for our preliminary tests, we chose one water year across 3 basins in the UCRB, the Yampa River Basin, the Blue River Basin, and the Animas River Basin. These 3 basins are subject to differing environmental conditions, and they also have widely varying distributions of snow climate classes, which embed hydroclimate information, land cover information, and elevation information. Okay, we'll first take a look at some SnowTel comparisons. So we're looking at the Blue River Basin in water year 2019. I've got all of the SnowTel snow depths for all the sites in the Blue River Basin plotted in this shaded gray. And right away, we can pick out that peak snow depth occurs around March 9th at about 2.3 meters. And melt out on the right-hand side here occurs between late June and early July over the course of about 3 weeks. When we add the National Water Model outputs for these same locations, we can notice right away that this pink shaded area is not building up enough snow. We're getting about 73% of the SnowTel peak, and melt is now constrained over a tighter range of about 1.5 weeks, but still within that SnowTel overall range. And when we add the HERMODIS outputs for these, again, these same locations, we notice that the accumulation and the mass representation is pretty good. We're still not hitting that SnowTel peak, but there are differences between points and spatial grids. But most importantly, we're seeing earlier melt out on the right of over the course of 4 weeks, and now we've been pushed into early June as well. So that was the Blue River Basin. Let's take a look at the Animas River. So this is water year 2021 now, and we see a different story. Both of the models in this test miss earlier buildups of snow. And then when we actually look at the snow melt out, we see that the National Water Model has a delayed and more prolonged melt out period compared to SnowTel. HERMODIS melted out earlier, but from all of these bits plotted on top of each other, we can see that they melted out differently for different reasons. Finally, when we move to the Yampa River Basin, this is water year 2020, we can see right away that both models had earlier melt out than the SnowTel sites, but again, through potentially different pathways. Again, the National Water Model is missing those peaks. It's not building up enough snow. And when we look at the steepness of those curves and the melt out, we're seeing that the HERMODIS implementation had a faster melt rate than the National Water Model. So different stories, different basins, but what is the same is the National Water Model is not building up enough snow, and HERMODIS is melting faster than both the National Water Model and the SnowTel sites. All right, so SnowTel gave us a really good snapshot of a really good evaluation of snow processes over the course of an entire water year. But we're going to move on to using ASO snow depth products to get more of a basin-wide context for this. For the sake of time, I actually have no idea how much time I have left, but I think based on my runs, we're short. I'm just going to focus on the Blue River Basin for this. Okay, so we are looking at the Blue River Basin, April 19th. I've got snow depth for ASO and the National Water Model in blue on the upper left-hand side. I've got the distribution of those snow depth values on the bottom left, log scale, if you'll notice. And we can pluck out right away that that lower buildup we were seeing in the SNOTHA comparisons, we're seeing that across the entire basin. This isn't just a fluke of those sites. In the distribution, ASO's shaded in gray, the national water models in that coral pink, and we're seeing the national water model pretty much capping out at about 1.5 meters. There aren't any values above that. When we take a look at the entire basin, we've got the national water model minus ASO snow depth in this snow depth difference map on the right. You'll see those differences represented in red values across the entire basin. The only exception to this under prediction is along areas that are north-facing slopes or along the bottom of valleys. When we compare the HER-MODIS implementation with ASO snow depth, we see a lot stronger agreement, both in the histogram, they're more similar, as well as in the snow depth difference map. A lot more yellows indicate more similar values between the two snow depth products. But similar to the national water model, we're also seeing these differences along slopes. South-facing slopes are melting out earlier, and north-facing slopes and along valley bottoms are in shades of blue. So more snow there in the model than in ASO. When we move to later on in the season, it's really then that we start to see the impacts of differences in resolution. So this is the national water model compared to ASO on June 24th. Again, overall, not getting enough snow. But the main exception is still those north-facing slopes where we're seeing these large blue pixels that indicate the national water model is building up as too much snow compared to ASO. And when we move to HER-MODIS, we again see better agreement. But we're also seeing quicker melts on south-facing slopes. That's a continuation of what we saw earlier in the season. Okay, so preliminary takeaways. We are, again, generally seeing an underprediction of snow for the national water model. This agrees with previous work and also motivates why we were doing this modeling in the first place. Our initial results are promising, but the current treatment shows that we are melting snow a bit too quickly, so there's more work to be done. But along the way, these ASO snow depth products will continue to be valuable for these basin-wide evaluation of model results. We're really excited about these results. As usually, we want to add more water years, more basins, test this out. But ultimately, we know that the quicker melt is due to issues with net radiation. So we're really excited to see what our cloud cover work will reveal. Thank you.
Thanks, Michelle. That was great. We have time for one very quick question. We have a hard deadline for our next speaker. So I'll give Ramesh a chance to speak and ask a question.
Thank you. It's a great presentation. I'm curious to know, like, were you able to go, and dig down into detail why the melting rate is quicker on hard-based, the MODIS model in comparison to a national water model?
I think I heard the question as, why is the HER-MODIS implementation melting faster than the national water model?
Yes.
Great question. I am not as familiar with the national water model workings as I should be, but for the HER-MODIS implementation, we suspect that albedo is actually a little too low now, despite the representation with the MODIS albedo products. It's a little too low, so it's getting a little bit too much net solar radiation and melting faster. So there's some more tweaks that we need to do. This is just the initial foray into new basins from the initial Easter River watershed tests. Thank you.
Thank you.
Thanks, Michelle. Okay, the next speaker is Noah Molotch, and he's going to be presenting remotely. He's a researcher at the University of Colorado Boulder, and he's a professor, and he has his own team, and we've been working with him for many years. Great, so I think, Noah, you can share your slides.
Great. I wasn't able to turn my camera on. The system wasn't letting me do that, but I presume that was part of your design, so I'll just go with it.
Thank you.
I want to talk about ways that we can enhance regional scale snow water equivalent distribution estimates with ASO data, and conclude with kind of a mission-based perspective on this. So this will be a little bit different than my previous talks at this workshop, and that, like Adrian, I want to talk a little bit more forward-thinking about how we can utilize ASO data. A number of my colleagues have contributed greatly to this work, many of them more so than I have, so I want to acknowledge the names that are shown on the screen here. The objective for a lot of my work in this context is to develop real-time spatial snow water equivalent estimates at regional scales. And for this talk, to illustrate some examples where we can leverage ASO data within our existing workflows to bias correct our modeled SWE. And while I'll show that there's a lot of value in the way we're doing that and what ASO is giving us, what I'd like to conclude with is some forward thoughts about how we can identify new workflows given the ASO sampling strategy that is emerging. So the SWE fusion system that we've developed through PhD work of Dominic Schneider and more recently Kehan Yang employs a generalized linear regression model where the dependent variable is snow pillow SWE from the SNOTEL and California Cooperative Snow Survey sensor networks. The independent variables in the statistical model include satellite-based snow water equivalent reanalyses, which are derived from a product that Steve Margolis's team that exists from 1985 to 2021, and additional independent variables that include various terrain metrics. And I've talked about this a lot for the California and Colorado audiences in the past, so I don't want to spend a lot of time on this. I want to kind of move this along. But this SWE fusion system was developed without consideration of ASO data. The primary value added was in leveraging the historical satellite-based SWE reanalysis. So there is newer technology and newer methods involved in the production of the snow water equivalent estimates. And more recently, in the last decade, ASO data have been extremely useful for evaluating initially our SWE estimates, and even more recently, bias correcting our SWE fusion data. And I'll revisit this concept here in a moment. So we've deployed the SWE fusion system over the Sierras. We've been generating operational SWE data since 2012 for the Sierras, and we're currently contracted by California DWR to continue doing that. Some example SWE maps here, many of you are familiar with. For those that aren't, please do reach out. We can get you on our SWE distribution list. This is considered complementary and augments ASO data where and when it's not available. We've also been producing these data for the Southern Rockies, and we did that operationally with funding from Bureau of Reclamation in 2022 and 2023. And we're now supported by Reclamation to deploy our SWE fusion system across the entire Western United States, where we've identified 5 distinct regions that will be analyzed independently, mosaicing these regions together to create west-wide snow water equivalent mapping. The clustering is based on some analysis that was led by Ernesto Trujillo, and the end result will be for this winter real-time SWE estimates delivered to the water resources community from February through May of 24 and 25. So the upcoming winter and the following winter, and potentially on into the future as funding permits. Now, the way that we've primarily worked with ASO data in recent years is illustrated in this workflow on the right, where we've got our model estimates shown by the orange tiles here. This is an example for the Tuolumne River Basin. We get ASO data. We can difference those to estimate our residuals across the landscape. And then we can do a pattern match exercise where for a current condition, we can identify dates in the historic past when ASO flew and then we can apply the error estimates from that previous date to the current date to bias correct our model estimates in real time. So it's like taking advantage of historical ASO data. And the way that we then model the distribution of these residuals, again, incorporates a number of topographic measures as well as our SWE estimates as shown by these independent variables in blue here. And Kohan has got a paper in review that shows that you can increase the performance of the model dramatically with this bias correction. Now, in real time, we have some additional challenges that and opportunities that I want to share with you, just some snippets on. So this is sort of our current workflow with ASO data. We model SWE. This is an example for the Merced River Basin for February 1st of 2023. An ASO data flight comes online around the same shown in the middle map here for the Merced. So we've got our model estimate, an observation from ASO, and then differencing them on the bottom map, you can see that there's a distribution of errors here, and we can transform these magnitude errors into percent errors, and with those percent errors, we can carry those forward in time to continue to bias correct our model based on this comparison with ASO data. Now, the basis, right, for translating the error forward in time, I think is well illustrated in the example that I'm going to show you here from the American River Basin in this last water year, 2024. And so the top row here is our SWE estimates for February 12th on the left, top left from our regression model. The ASO estimated SWE in the middle, and then the difference showing the error in our model on the far right. You can see our models underestimating SWE more dramatically in the highest elevations, overestimating SWE in the lower elevations. The same thing is shown for a date at April 8th for our regression model on the bottom left, ASO flight on April 10th. And when you look at the error structure, you can see that it's following a very similar pattern to what was observed in February. So the leap of faith, right, that this error pattern observed in February could potentially be used to bias correct our model in early April is supported by the similarity in these two error maps that you see in this slide. So when we then transform that to the at the top left, the ASO data in the top middle, and then that same error pattern that you saw in the previous slide on the top right. And then here on the bottom left is our bias corrected ASO, linear regression model estimate on April 8th, utilizing the ASO data from February. That ASO data on April 10th, again, shown redundantly in the bottom middle. And then the difference map now where we're comparing the bias corrected SWE estimate that's bias corrected based on the February acquisition versus the April observation from ASO. And so the comparison here is to look at the top right map versus the lower right map, where you can see those magnitudes of the underestimates and overestimates in SWE is dramatically reduced when we deploy this bias correction scheme. Okay, so that is all this rabbit hole that we've been going down with ASO data that we're very happy to do and that we've enjoyed doing. But it's occurred to me now with a few years where ASO is becoming sort of a mountain range scale and starting to verge on a regional to continental scale observing system, is to rethink the way we use ASO data and SWE fusion from the perspective of ASO as a suborbital mission. So we've started with the Tuolumne River Basin on the order of 50 plus flights. We then transformed our workflows to start with ASO data at mountain range scales. And now that we're supported to work at the regional to continental scale by reclamation, it behooves us to sort of rethink the workflows that we've established based on starting at the watershed scale and then going to the mountain range scale. And this question I pose here at the bottom is apropos to this. Like, how do we utilize ASO data in an elegant way to estimate SWE over larger areas, and to evaluate that question without thinking about the way we've been doing things in the past, but this mission concept, right? So if we were thinking about ASO as a suborbital mission, we might think about it in the construct of how a satellite mission is developed, where, you know, these lines roughly represent, and not accurately, but they're just for argument's sake, swaths, right, that a satellite would pass over the land surface, where we would, as a mission is developed, establish measurement requirements with accuracy requirements, spatial resolution, temporal resolution, and other considerations. ASO already does a great job with accuracy requirements, and we know, of course, what the spatial resolution is. The temporal resolution is dictated in part by constraints associated with weather and flight availability, as well as airborne assets. In the context of a mission, we would also be thinking about product development from level 0 to level N, and ASO is, of course, developing all of their wonderful products that are just pushing the community forward in great ways. But in a mission concept, we would also be standing up a science and applications working group that would be considering what the measurement protocols would look like in the context of how we could most efficiently and robustly apply those measurements to the societal challenges that we face. And so in the reflecting on the Sierras, right, where now we have effectively on a sort of 3-week interval, ASO data covering nearly every watershed of the Sierras, the way that I work with ASO data and have over the past few years, the way I have been working with it versus the way I should be working with that data probably evolved differently if 5-10 years ago I started planning, like for a mission planning, as to how I would utilize these data. And so I think it's a ripe time to be thinking about a 10,000-foot view of how we utilize ASO data. And so I'm starting to think about SWE Fusion sort of version 2, and we're kind of just in beta mode of thinking about this, but thinking about ASO potentially as the dependent variable, not for bias correction, but actually training our model with ASO data. That's one option. Another option is to include historical ASO data as an independent variable in the statistical model, and to be thinking about how we can combine ASO data with emerging remotely sensed data, such like that'll be coming from NISAR, which is a satellite that's going to be heavily constrained in terms of where potential SWE measurements can be made, but nevertheless, potentially some value there to be brought into the fold as well. So in summary, I really see this as an important time to address this main point I have here at the bottom. How do we learn from the past in terms of how we worked with ASO data? Project into the future without knowing exactly what the ASO measurement program will look like, but maybe with some targets. And then from that, design efficient and robust workflows. And in the context of the work that my team is doing, I think that's just one example, but would really love to engage in broader discussions with the community about how all of our minds can be brought together to address this important problem. And with that, I will conclude. Thank you.
Thanks, Noah. Noah, do you have time for a question if somebody in the
I
audience?
do.
Okay, perfect.
Hi, Noah. It's Eli Boardman. My question is, with these sort of data-driven reanalysis products, I'm wondering about like using more machine learning approaches like a deep neural network as opposed to the linear model, and whether you've tested that and found whether the results versus complexity trade-off is favorable or not.
Yeah, that's a great question, Eli. Thank you. So, and I forgot to mention this, but the I think the opportunity the limitation, in my view, of deploying machine learning algorithms with our current setup is that our training set is from the snow sensor network, where the sample size at the subregion scale is just not significant enough to where you run into problems of model overfitting really quickly. And by bringing in new sources of information, such as ASO data as part of the training set, and potentially measurements from NISAR, I think that the opportunity to deploy machine learning algorithms then becomes a very real possibility. And that's, again, the direction I think that for Sweet Fusion 2.0, that is where we're going to be going. Thank you for that question.
Great. Thanks, Noah. Okay, the final speaker for this morning is Amy Clark. She's probably come the furthest than anybody here, her and her advisor Nick over there, all the way from the UK. So from Northumbria University, we've got Amy Clark. She's going to be talking about canopy and snow and sub-canopy snow.
Yeah, so hi, I'm Amy Clark and I'm a PhD student. I'm co-sponsored by ASO. And Jeff Deans is also one of my supervisors, and I'm working with Nick Gritter and Leanne Way, also based in Northumbria University. So we're looking at forest canopy effects on simulated sub-canopy snow in an operational snow balance model. So as all of you know in this room, like the snowpack in the West is very important for water resources, so that's why we're modeling it and care about it. And we all probably also know that forest fires are increasing as well, so it's kind of changing the structure of the canopy. And the canopy is a major, or like strongly controls the dynamics of the snow energy balance. So yeah, we want to look at how sensitive snowball is to, how sensitive is snowball simulated suite of forest canopy parameters. So this is a quick schematic just to kind of help you guys conceptualize sub-canopy snow forest energy balance. And starting at the left, you have kind of your mass input, which is your snow input, you have your canopy interception and your sublimation and unloading onto the snowpack. And then from that, you kind of have your energy balance, which is where you have your shortwave radiation coming in, you have your canopy shading, which kind of reduces the amount of energy getting to the snowpack. And also from the canopy, you have long-wave radiation being emitted. And in addition, you also have wind, which can blow the snow, and the canopy can reduce that wind. Kind of going along, you have disturbance effect, like events. So you can have fire or like beetle infestation or even management. And this changes the canopy structure and changes what is like going on. And from this, you have an impact from the disturbance event. So you have reduced interception of the snow, you have reduced canopy shading, and you also have like black carbon and Albedo. Yeah, so the impact of disturbances kind of reduces the amount of interception as there's less like canopy there. You're kind of left with these like just cocktail sticks that we like to call them. And so more snow lands on the ground. You also have reduced canopy shading as there's just like no canopy there to sort of protect it. So you have higher shortwave coming onto the snow surface. You have black carbon, which lowers the albedo, and all these kind of factors alter the timing of melt because they're altering the snow energy balance. For this talk, we're specifically focusing on the incoming shortwave radiation and the canopy shading, that's going on and everything, to kind of answer how sensitive are snowball suite simulations to do two different approaches to vegetation height estimations from LiDAR. So here on the left-hand side, we have the workflow for kind of this model setup. And you have your above canopy, which is your met data going in. You have your canopy height model, which is representing the canopy, and that's also fed into the data. You have an option of 3 parameters for the canopy. So you have veg-tau, which kind of deals with diffuse radiation. You have veg-k that deals with direct radiation, and then you have your canopy height. And your veg-k and veg-tau are derived from land fire values, and the vegetation height is from ASO canopy height models. And this produces a sub-canopy shortwave energy to like the snow, and these are spatially variable but temporally static, so they don't change with time or anything. And then from that you get simulated snow in snowball, and snowball's the point model of ice snowball, so that's just what we're using just to sort of test it and run it in like kind of a smaller point scale rather than the whole basin. So veg-k and veg-tau are derived from land fire, and you essentially have kind of 5 pairing options for these values shown here, and this is from Links and Marks in 1999, which is when they developed these pairings for vegetation or canopy class. And here's just a quick example of you have sub-canopy shortwave on the y-axis and then the different vegetal values along the x-axis. And the lines, like the dashed lines going down, kind of show where these values intercept with that sub-canopy shortwave. So you can see all the vegetal values are kind of clustered towards the bottom end of it. So you don't have many options for where they are. And then the same again for veg K. These are a bit more spread out, and it's important to note that vegetal has a linear relationship and veg K has a non-linear relationship. So to test this, we're kind of looking at the San Joaquin, and this is the study site. We have 4 sites that we're kind of running this like toy model, like this snowball on, and yeah, we have short, sparse, short, medium, and tall, and these sites were all chosen because they have different canopy heights, and they also post-fire they had different burn severity, like in the fire they had different burn severities as well. So I start looking forward to the like post-disturbance, we have different burn severities to look at. And then here is the ASO LiDAR data for these sites, just kind of showing again that they're all kind of different structures and different heights throughout the canopy. So ASO's canopy height model is derived by like through 2 ways. So you have your maximum return and your average return. So these are different ways of processing the LiDAR data, and you can get different canopy height models from this. So the average return, you take one of them 3-meter ground resolution pixels and you average that out and get that value. Or for the maximum return, you kind of take the highest LiDAR return point, and then that's the value for that whole pixel. And so this kind of creates a change in the parameterization of the canopy within the model, which kind of gives us a great opportunity to test how sensitive the model is. And it's just important to know that neither of these like ways of deriving the canopy height model is right or wrong. They're both used for different reasons within ASO, and it's just different ways of estimating the canopy. So here on this slide, this is a histogram plot of each of them sites. And on the y-axis, you have the count. So it's each one of them squares kind of height value. On the y-axis, you have your height. In the orange, it's the average return. And in the blue, it's the maximum return with the median plotted on the, and this like, I like this graph because it shows the differences in the heights between each of them sites, but it also nicely shows the shift in how much there is a change with the different LiDAR processing options. And here's some stats on it. So the sparse site is only a 1.46 meter increase, but that's about a 383% increase, whereas on the tall site, it's an 11.99 meter increase, and that's about 50%. So these are like quite big changes, and it's also important to note that the maximum canopy return hasn't been slope corrected in this data, and that'll probably bring it down a bit more. So, but yeah. So yeah, for the model experiment, we just kept veg K and veg tau the exact same, and ran a 50 meter square, and just changed the height. So we changed it from using the average, and then changed it to the maximum. And here are the results that we got. And yeah, so we've got simulated snow on the y-axis and then time along the y-axis. And I think the most important takeaway from this graph is that the biggest difference is when you have short and sparse vegetation height. So when you've got like you kind of medium and tall, so you higher, kind of more denser forests, they're kind of less sensitive at the parameters. And then on the next slide, this is just a plot of the differences between the two. So in the sparse site, it's kind of up to about 0.8 meters, and then your short site is 0.2. And then on your medium and tall, it's as little as like 10 centimeters for both of them. So very small, and that could even just be like the noise in the model. So to conclude, the way that you process the canopy height models does have an impact on the model, and sensitivity decreases as height increases, but the model is sensitive to when you have that sparse and shorter vegetation height. So I kind of started off talking a little bit about disturbances. These will create more forests with short and sparse canopy heights. So kind of the fact that the model is more sensitive to this, and you kind of got to investigate what's going on and why that's happening. And I want to draw your attention to the workflow that we had before and kind of talk about my future plans. So if you remember, I said that these are temporally static parameters. What we want to test is using CanRad, which creates a synthetic hemispherical photograph of points, and then also calculates ray tracing across it. So you get a temporally variable canopy parameter. And we want to test if that can improve like simulated sweep. Hopefully it will. And we think that kind of will have a more effect on when you have the sparse and short canopies. So yeah, that's everything. Any questions?
Thanks, Amy. That was really great. I have some questions for you, but I might hit you up later in private. Is there any questions from the crowd? Matt, we have Matt over here. And while we're getting Matt set up, I do want to say that the snow model is what M3Works used to drive the density piece of the ASO workflow and then to sync the flights together. And so this kind of work that Amy's working on now will help us parameterize these models going forward to take into account things like fire and in big impacts like that. So it's super exciting for us to see this work. Who's Dan speaking? All right.
Is it on? Looks like it is. Thanks. Really interesting talk. I'm Dan Beresford with ASO. Just curious about the CANRAD modeling going forward. So is that generated from aerial photography, i.e. would we generate it with the photographs that we take using our RGB camera line, or like how is that generated?
Yeah, so it's generated from, you have CANRAD, which is kind of overall model, and then there's two options. You can derive it from LiDAR data, which is like L2R, which is kind of like LiDAR to radiation, or you can derive it from just a canopy height model. So that's kind of C2R, so you've kind of got those two options. So it's kind of more like the LiDAR data that you're getting the values from.
Questions? Matt's question's still burning.
So you're working in an area that had extreme change to vegetation type. And I'm wondering how this will change over years, because that sparse vegetation type is likely to have a larger proportion of height change than the tall vegetation type. So that's something that would be really neat to look at as this changes over the year. Depending any method that you do, just repeat it over the years and then see if that error goes down or if it maintains, because that'll give us a really good sense, especially for Chad, where his basin is 40% burned or whatever, how long it might take to get back to some sort of normal.
Yeah, definitely. I think regrowth is definitely something that we'd like to look into as well. So yeah, thanks.
Yeah, and then following up with that, I think like if you can have like some sort of simulation, varying from, different heights, and then have that simulation, keep working on that such that like, if or when that the impact ceases to zero, if you can find that, I think that would be awesome to see, because the impact of HDS is, a lot in our watershed. So
yeah, thank you.
Good work. Thank you.
Great. Thank you so much. We are also working on some regrowth things internally as well, like looking at how quickly the landscape does bounce back from a fire and what that looks like. So great question there. Okay, we're going to jump into a coffee break, 10-minute coffee break. So be back here at about 22 past, if I'm going to be specific. Thank you, everybody.
All right, we're going to go ahead and get started now with the modeling session. We've got a two-part modeling session. Part one this morning, the exciting conclusion this afternoon, so you'll have to stay tuned to see what happens. It's a cliffhanger, promise. But our first speaker of this session is Eli Boardman, and now for something different, talking about ASO applications over glaciers, which is pretty cool. Take it away.
Thanks. Hi, everybody. I'm Eli Boardman. I'm technically still just a PhD student at UNR, but today I'm actually presenting on behalf of my LLC on the first year of our project in collaboration with ASO, applying the snow and glacier LiDAR to Wyoming. This is part of the Reclamation Snow Water Supply Forecasting Program organized through Mountain Hydrology LLC, but with a whole bunch of partners, as you can see. And the goal is to acquire 3 years of ASO data in the Wind River Range, Wyoming, and deliver real-time streamflow forecasts to various stakeholder and management groups. So today I'm going to talk just briefly about some of our operational results from this year, but then spend most of the time kind of focusing on some of the sciencey results from our first year of snow and glacier data. So looking back at our operational season this summer, Wyoming is very cold and snowy, so our season is shifted a few months later than most other seasons. So our ASO survey was on May 31st, which was really ideal timing, right about peak SWE this year. You can see that picture from late May. That's around 10,000 feet, still snowing and accumulating there just a couple days before the ASO flight. We also did a whole bunch of density field work, 25 snow pits up to 13,000 feet to really constrain that snowdrift heterogeneity and densities. And then these snow data are assimilated into DHSVM with a process-based method that avoids mass balance violations. And then that ultimately provides ensemble streamflow forecasts for 10 different watersheds. And some of those forecasts were directly used to manage the water releases from their largest reservoir in the Wind River Range, in addition to several smaller reservoirs on the Wind River Indian Reservation. Just looking at some of our forecast results from early June, we did capture the true value in our confidence bounds. The true value ended up kind of toward that 90% exceedance level, and that's largely a result of a very dry summer in Wyoming. There was almost zero summer precipitation. And it really shows the value, of that ASO data at the start of the melt season to constrain that low to no precipitation end member of the forecast ensemble. Looking at this on a daily time step, you can see kind of the evolution of our uncertainty over the season with these forecasts being updated about weekly, ultimately converging to kind of a daily NSE around 0.8, 0.85. All right, so that's actually all I have for the operations results right now. I'd love to talk more about it later if anyone's interested. But I want to spend the bulk of my time going over some of the glacier and snow science results that Adrian teased earlier. This is a picture from June of this year in the Wind River Range, just a couple weeks after our ASO flight. And you can see it's a very snowy and glaciated mountain range. Actually has the largest glaciers in the US Rocky Mountains. But like most mountain glaciers globally, they're rapidly melting. This summer, I actually recreated a mountaineering expedition from 100 years ago, went back and climbed some of the same peaks, took some of the same pictures, and you can really see how dramatic the glacier change has been in that 100-year time period. That picture on the left was actually kind of challenging because the glacier has melted so much vertically that you can't even get the right perspective on the mountain anymore. I also wanted to touch on a little history of the Wind River glacier research. Some of you may know Mark Meyer, was a really eminent American glaciologist and really advanced the study of mountain glaciers and their importance globally. He was also a really early adopter of remote sensing for snow and glacier research. What you might not know about Meyer is that his first ever glaciology project was mapping the Wind River glaciers for his master's thesis in 1951. It was also the first real Wind River glacier research. So that picture on the left is a hand-drawn map from Meyer's 1951 master's thesis of the Wind River glaciers. And I also wanted to really thank ASO and specifically Tom for really advancing this, carrying on Meyer's legacy with the mountain glacier remote sensing with a very sizable in-kind commitment to monitoring the glaciers both in Wyoming and elsewhere. These are really important data for understanding the climate and the cryosphere. And ASO is really doing a tremendous public service by helping to acquire these data at a reduced cost with this large in-kind commitment. So here's a quote from Meyer's master's thesis. He's talking about why there's some of these glacier remnants down at low elevations, much lower than the large glaciers in the Wind Rivers. And he's suggesting that the topography is driving enhanced snow drifting that contributes to the persistence of some of these small glaciers at low elevations. And while that's intuitive, it took another 80 years before ASO was able to really map this effect at super high resolution and show that, of course, Meyer was right. So this is the most sustainable or slowest melting glacier in the Wind River Range, but it's also one of the lowest elevation glaciers. And the reason for that is because it has about 12 meters or 40 feet of snow depth accumulation in that accumulation zone. It's drifting off of this massive windswept plateau above there. But we don't just have this data for one glacier, we have it for the whole mountain range. And so this really allows us a unique opportunity to evaluate the spatial heterogeneity of the mass balance of all these different glacier features. We have the first year of ASO glacier data from 2023, and we have a previous USGS LiDAR data set from 2019. And by comparing those, we can kind of approximate the vertical thinning rate over about a 4-year period. And then from that, we can estimate the mass loss from that ice that's melting. So here's a plot of a bunch of different glacier features at different elevations. We're showing kind of the hypsometry of the snow accumulation versus the mass ice melt rate. And the one thing you can notice is that the larger glaciers are generally melting faster, and that the smaller glaciers have deeper snow drifts. The thing I think is interesting here is that the deepest snow is actually at the lowest elevations. Now, part of this, right, is a selective sampling that if I'm only plotting points from glaciers, so the only glaciers that exist at low elevations are those that have really deep snow. But there's more to it because you notice that at the high elevations, there aren't any of those super deep snow depths, right? So it's not just a selective sampling effect. There's also a real effect that there's deeper snow on the lower elevation glaciers. There's also about an order of magnitude heterogeneity in the year-over-year mass thinning rate of some of those small features. So to investigate some of that heterogeneity, we can invoke different topographic metrics to look at some of the controls on the mass and energy balance. I promise I'm not going to go through every one of these panels. If you want to read that, you can just read the paper. What I'll do is I will show some photos. So one of the controls on the energy balance is elevation, right? Because at higher elevations, it's colder, so the ice is melting more slowly. Another control is shade. More shaded glaciers have less radiation, melt more slowly. But in the wind river range, wind drifting turns out to be perhaps the most important single process. And this really drives the persistence of some of these cirque glaciers at low elevations. So here's a map of some different of those topographic indices for two different glaciers, a cirque glacier and more of your typical valley glacier. And you can see that the cirque glacier really has that greater solar shading and enhanced wind drifting. And as a result, we get exceptionally deep snow accumulation and a much slower ablation rate, even though it's at a lower elevation than the valley glacier that's melting faster. We can look at this across the entire landscape for all of the glacier area, and we can categorize the dominant terrain factor for different glacier pixels at the 3-meter scale. What we see here is that for glacier area with more than about 3 or 4 meters of SWE, it's almost entirely the result of wind redistribution. Those are wind-dominated areas. Whereas the glaciers that have less than about 1 meter or 2 of SWE, those are largely elevation-dominated glaciers. And those are most vulnerable to additional climate warming because they don't have the extra accumulation to make them melt more slowly as they start to melt faster when it gets warmer. We can also think about this at the scale of full watersheds. So we have 5 gauged watersheds that are adjacent here, and they have variable glacier area fractions from about 1 to 7%. And when we normalize the streamflow hydrographs from these watersheds, we get this really compelling stratification of the late summer streamflow. So the watersheds that have more glaciers make much more late summer streamflow. And you might say, okay, that's obvious because they have more mass loss, right? So as the glaciers are melting, the glaciers are contributing this kind of unsustainable source of meltwater from the ice that's being lost. And that extra ice is especially concentrated in the late summer, because that's when the seasonal snow has all melted. And this does match the stratification by the glacier area with a pretty high correlation. However, with the ASO glacier data, we're able to estimate that mass balance flux. And it's basically way too small to explain this interwatershed heterogeneity. So when we subtract the mass loss rate out of the hydrographs, we see that that stratification remains. So even if there were no glaciers, the watersheds that currently have the most glaciers would still make about 1.5 times as much August-September streamflow as the watersheds with fewer glaciers. So there's some much more underlying fundamental heterogeneity between these watersheds beyond just what glacier fraction they currently have. To understand this, we really need to look at the high-resolution snow data across the entire watersheds. This is different snow metrics for the 5 watersheds, and I want you to really pay attention to the 2 watersheds on the left that are highlighted with the red star. Those watersheds have relatively less total snow storage, but much more deep snow storage, and correspondingly more glaciers. So there's this inverse correlation between the volume of snow in a watershed and the amount of deep snow in the drifts. This is ultimately a result of orographic precipitation, where the west side watersheds get more snow, but it's relatively thin, and the east side watersheds are having very high winds with less snow, possibly due to sublimation, but what snow they do have is in really deep, persistent drifts. When we renormalize the streamflow hydrographs by the different snow depth metrics, we find that those deep snow depths really do explain most of the remaining interwatershed heterogeneity in the late summer streamflow. The thing I think is really fascinating here, though, is that there's actually a fairly strong negative correlation between the volume of snow in a watershed and the amount of late summer streamflow that it's producing. So let me say this again. The watersheds with more snow make less streamflow in the late summer. So it's like the opposite of the grammar plots, right? This is like the inverse. More snow makes less water. And the reason for that is we have to consider this, this inverse correlation between snow volume and the amount of deep snow storage as a result of these topographic effects. So when we instead just consider the snow volume stored in deep areas of the snowpack, then we have a very high correlation with that late summer streamflow heterogeneity. It also really highlights, right, why we need these distributed depth measurements. If you were doing this off of something based on just like snow-covered area, you would actually get this inverse correlation between more snow and less streamflow. So just to summarize some of our results in the Wind River Range, the glacier mass loss on that 4-year period from 2019 to 2023 was about 12 to 39% of the August-September streamflow volume, depending on which watershed you're looking at, and kind of 1 to 7% glacier area. So this means that as the glaciers either vanish or re-equilibrate, you lose that unsustainable ice volume, and there's a considerable potential for reductions in the future streamflow volume. However, that will not remove the interwatershed heterogeneity, because of this underlying factor of the topography and the interaction with the wind redistribution. So in other words, the watersheds that have the most to lose also have the most to keep. They'll still stay ahead. They'll still make the most water. And moving out to a little bit bigger picture, I've read a lot of different studies that kind of contextualize mountain glaciers and glacier recession as something that sort of happens to a watershed. But I think of glaciers really as something the watershed does, right? It's a result of the interaction of the large-scale climatology and the watershed by watershed topography. And so especially in really wind-dominated areas like the Wind River Range, both the glacier abundance and thus the non-renewable streamflow and the underlying snowmelt patterns can both result from this heterogeneity in wind processes. That's all I'm going to say for now. There's a lot more research to be done here. We're looking at geomorphology aspects. I also, earlier this week, I actually coupled DHSVM to a fluid dynamics model. So we're going to be looking at some of the process-based elements of the wind redistribution. But hopefully there'll be a lot more results to share at future ASO workshops. And for now, I'd be happy to take any questions. Thank you.
Excellent. I got a question, but let's throw it out there. Gus, where's our mic man? There he is. Mic person.
Thank you. Thanks, Eli. I always appreciate your presentations. I just want a clarification. So that part about the basins with more snow had less water, but that was just late in the season.
Right.
Overall, they still had more runoff.
Right. So if you look at this plot, I didn't really have time to dive into this, but it's looking at the differences in streamflow production relative to the cross watershed mean as a function of the day through the summer. And of course, that like May through early July period is best explained by the snowpack volume. So yeah, the watersheds with more snow do make more water, but only early in the season. And if we look at those normalized hydrographs, you see that stratification where the watersheds with the most snow are high in May, June, but that really flashes off quickly, and we're really looking at that late summer stream flow. Part of the motivation for really focusing on that is that the Wind River Range really has low artificial storage capacity, so that we don't have reservoirs that can last very long. So this late summer stream flow is really important for like agricultural resilience and meeting that demand or not in the future climate. So ultimately, we're going to be looking at whether, you know, the climate change and the glaciers and the wind drifts can or cannot meet the future agricultural demand.
Thank you.
Quick question. Can you rule out dipping bedrock from one side of the range to the other as a reason for this? Like, well, why one side is getting this preferentially high, but your inverse signal basically.
You mean as like a subsurface mediation, or,
yeah,
or in
exporting
the snow
melt that's
distribution?
coming over here and pushing it over to the other side as a base flow? When you start
and
looking
then
at the low flows, you
it's
kind of
interesting. I think, I mean, in general, it's a granitic range. So we would expect shallow groundwater. I mean, it's possible, right? Maybe someone give me a ton of geophysics funding. We'll go do the deep seismic surveys. But yeah, I suspect it would be very minimal because it's a granitic fault block range.
Sure. Any last quick questions? All right, that's it. Next.
Thanks.
Yeah, so we have Alkire, Eckberg, Kollen, and they're going to be singing off their new SnowTrax album, I think, right? Is that what it is? Okay. Greatest hits.
Hello. Is this thing on? It is. Sweet. So some people call me the toothless hippie redneck punk from Oregon, but you can call me Jacob. I'm here to present on a project we kicked off last year that we're pretty excited about. It's called SnowTrax. It's a website, and I'm here presenting alongside some awesome colleagues and strong code contributors. I'll just kind of go over the sort of the project fundamentals, and then Lauren will kind of talk to the bulk of the existing content, some new sort of 2D looks, and Devon's gonna follow up with a pretty sweet spatially explicit dashboards that are a little bit whiz-bang, a little bit more applicable to this audience, so we'll kind of leave on a high note there. So what is it? As I said, it's a website. If you navigate to snow.water.ca.gov, you'll see something like this. It's a your splash page. You're starting to see some images, quick summary stats, some bullet points, some high-level information about the California Cooperative Snow Surveys Program, its charge, and which I'm going to focus here on bullet number 2, which reads, facilitates the cooperative sharing of data amongst California water management agencies. So we're agency, and that's our charge. That's our group's charge, and that's kind of what we're leaning into with this tool that we built out. And basically, we just made a lot of really sweet interactive data visualization dashboards that we're really proud to share. So we'll kind of zoom in on that as well. But it's all oriented around, what we were set out to do about 100 years ago or so. So this is a long-standing tradition of being providing data and a sort of a data store for transparent water information in California. So I'm going to kind of talk to the project fundamentals here. And I just want to give a quick shout out to Sean de Guzman. He's not here, he took another job, but he was a manager at the Snow Surveys Water Supply Forecasting Unit here at the California Department of Water Resources. He was under a lot of pressure from above, and he's a really strategic thinker, and he provided us a lot of cover, if you will, to be able to establish this project in, well, it's non-traditional from an agency perspective, let's say it that way. And so these are some of the fundamentals that are intended to kind of, at least from my perspective, reduce some of the typical inertia that you find in agencies, if you will. So let me kind of talk to them. Increase transparency. So we get a lot of, we do water supply forecasting as well. So people are like, hey, why'd you make that call? And we're like, well, the data. And you're like, show me the data. We're like, okay. That's basically it. So we make a lot of decisions on our input data streams, on our big decisions, and there was just a call for just show me what you're working with a little bit more. So that's a big intent here. As in any project, it's really nice to have a focused audience, and that is the California Cooperative Snow Surveys program as a whole. We've got observers, we've got researchers, we've got water agencies that are in flood responsibilities, we've got agencies that are water allocators. As part of this larger cooperative, we have an annual meeting in November. You guys can come to it if you want to learn more, but that's our audience, and that's how we're kind of orienting our tools towards. We've also adopted some open source principles. And so all of our dependencies that we've built this off of are all open source tools. We've committed our repository to being an open source project. If people want to contribute, we let them know, hey, your code base is going to end up on an open source thing, just so you know. We don't have it like, you know, in a public facing GitHub repository, but we are open to sharing it upon request. This is one of my biggest observations of a lot of our technology infrastructure when I started this job, is that a lot of our tools were built by one person and not the same person, and they retire, they take other jobs, they're not responsive, and it really kind of creates a lot of barriers to changing things, improving things, developing things. So one of the ways that we do this is that we just, you know, we had a pretty poignant question, I think about a year ago, is like, how do we code as a team? We were just kind of, everybody, it was a bunch of individuals coding, doing their own thing. And we asked ourselves, like, how do we do this like at like a teamwork, team style coding? And that question, we adopted some standards. We also adopted GitHub repository management for that code base. And that's enabled us to be able to have 3 people contribute, have people who get hired on that want to contribute, and they can have a great, they can quickly adopt that and contribute. And so we've got up to, I think, about 6 internal developers, and we've also started to work with our contractors as well, and says, hey, do you guys want to contribute to this? So now we're an inter-organizational code base. So we have multiple developers across organizations currently, up towards about 7 or 8, hopefully to provide, well, diversity in perspective, but also just resilience if somebody moves on or gets busy with other work, that we can kind of keep this machine rolling. Another bit here is our agile project. And what I mean by that is that you could build these things as complex as you want to. You can make it, adopt a database, make it super abstract, or you can kind of keep it really straightforward and simple. There's costs and trade-offs and everything, but the trade-off we decided was agile. So make it approachable. So you're young programmer, maybe you're a civil engineer that's like picking up some programming, which is like the bulk of our contributors, and you want to be able to, something understandable to contribute to really quickly. Simple CSVs in a folder, something like that, works. It works. And so we kind of adopt that style for the sort of to make ourselves open to, again, multiple developers approaching this project. And a strong endpoint here is community driven. So we are for our cooperative. We're also driven by our cooperative and others as well. And what that shows up as, basically, let me just tell you a story. Our flagship dashboard, the snow product comparison dashboard, was one that there was we had a serial dashboard developer about 5 years ago, just like make a bunch of dashboards. He took another job, and I just started this job, and we basically, let's get that going again. But we basically, there was, while you're going on that, I'll just kind of keep riffing. Basically, there's one dashboard that everyone kept asking for. They're like, hey, when's the snow product comparison dashboard going to come up and like be operational this year? And we had, the guy moved on. They're like, anybody know how to do that? Like, no, but I'll give it a go. And so that was like a community driven, like, hey, we want that back sort of thing. And I noticed that that dashboard, A, was not automated. B, it was on a Tableau thing that had a bunch of license blocks to it. And it was buggy. If you look at it wrong, it would break on you. And so anyways, one of the big things we did here was take what the community was saying, hey, we need that back, and put that in solid foundations, which is kind of the impetus for the larger project. But then we also kind of, in doing so, built a platform to host a bunch of other dashboards as well in a sort of a more stable environment. So community driven, we'll ask for your feedback at the end of this presentation. If you see things you like, things you want to do differently, please give that to us. That's how we improve. And that can show up in a bunch of different ways, whether you're an annual commenter, like the bulk of our cooperative at the end of the forecasting season, we ask, solicit a bunch of comments. We've got some great stuff. We've implemented a lot of that. We'll show a lot of that. Whether you're a serial commenter like Gabe over here that spends a lot of time trying to like perfect things, make things better, we would appreciate more of that from others. That's how we're going to get this thing super whiz bang and polished. Whether, we also want to shout out and invite to visionaries out there, whether you're a researcher or somebody like a Chad Moore out there that just like things that come, that haven't been there before. Boom, we would like those ideas. We can make that reality. And maybe you're like a practitioner that's been in the game for decades, and there was like this one plot like 5 years ago you saw that was super helpful that you thought would be useful to the larger audience. We can adopt that and make that available. So maybe like a Gus Goodbody or somebody like that. We'd appreciate all that feedback. I'm going to give you a quick couple status updates on non-SnowTrax stuff, just because this is stuff we've talked about. We've been in charge of deploying GNSS occupations across our snow course and our snow pillow network. I said it was about 5 to 6 years last year. For completion, we're about 15% collection this 1 year since then. So just a status update. Not too bad for government work, but we're getting there. Another one was there's an instrumentation information Java application coming out. That's from our statewide monitoring network unit. And it's just more detailed information about what is where in our micrometeorological network. So rather than just saying you got SWE, you can say, hey, I got a pillow or I got a scale. I got rain gauge, I got some precipitation. And well, what type of gauge are we talking about? Even drilling down into the details, get the make and model of the instruments that are present, the locations of specific observations. So my rain gauge is over there, my pillow's over there, sort of thing. And the height of observations where it's useful. So my input to my gauge or my anemometer height, things like that, to hopefully make this information a bit more high-end, if you will. And with that, I will transition to Lauren Alkire.
Thank you, Jacob. Good morning, everyone. So I'm going to move us on to dashboards. So the first dashboard that I'll be talking about is pretty much a new dashboard, and then the latter 5 are all ones that are already publicly facing on our website, but I'll give an overview and then a few upgrades that we've made to those. But before I do that, just wanted to give a brief interlude to something foundational to all our dashboards, which is data access. So if you use CDEC, you may already be aware of this tool, but it's just a super easy way to get a lot of tabular data all at once. So if you go to that Query Tools tab, and then down on the bottom there, that historical data JSON CSV format, you click on that, that'll take you to this page, and you can enter in comma delimited stations. So you could list all 15 snow pillows in your basin, and then select sensor 82 would be QC snow, QC SWE. Select the time period, and then if you use the JSON or the CSV data link, that'll output a URL, and those URLs are really easy to modify. So if you wanted it in a scripted process, that's an option. So just super handy way to get data off of CDEC. Now, I'm going to go over to dashboards. So this first one is a late iteration of a dashboard that we've used internally for a few years now to do our snow pillow QC process. So as Jacob mentioned, a lot of the effort here is just to be more transparent with what we are looking at when we do our daily snow pillow QC. And hopefully this is something that will be useful to all of you. So it's not public facing quite yet, but it will be for this season. So I'm just going to go through what's on here. There will be some more cosmetic changes, but this is mostly towards the finished product. So at the top here in the title, we have the station name, the basin, the elevation, who maintains that station, the precipitation as a % of the water year average, and the SWE for the current date as a % of April 1. There's also a date selector here, so you can look at a wider or shorter time range, and there's a water selector there on the side. I'll go through what's on the plot because there is a lot of data here. So On the primary y-axis, we have water equivalent, which on this plot is SWE and precipitation. And then the secondary y-axis, we have depth and density. So I'm going to go through all of the little items on here because there are quite a few. So first of all, those blue diamonds here are our control measurements. So if the pillow has a control, it'll be plotted on this dashboard. We also have the 4 nearest grid cells for ASO SWE data. And then in orange here is the QSeed SWE data that is coming out of our shop. Then we have depth data. We both have a daily is this thick purple line, and then the hourly plots in a thinner purple line. We've got precipitation as a daily accumulation, as well as an hourly accumulation. Density is this bright green line, and then this bright yellow line is CNRFC QPE. The raw SWE is also plotted on here at an hourly time step. And then we have daily incremental precip here plotted in those bars at the bottom. And then lastly, these are the 4 nearest grid cells for the DWR ice snowmelt model. So yes, coming soon this year, but not public yet. And then onto another dashboard that you may have seen previously. This is the Snow Pillow Quantile Time Series dashboard. So this is very similar to an NRCS product, but you can see the quantiles, the historical quantiles for SWE for a given snow pillow, and then you can turn on and off different water years to plot on top of each other here. We also recently added the ability to select either like a basin, a region, or a statewide number. So it's basically just going to take an average of the snow pillows that are within whatever region that is. A little slow today, not normally quite so slow. Then for a couple updates that we are going to be putting up across all of our dashboards have just been pioneered on this dashboard. So the first of which is metadata. So this is a little toggle basically where you can get metadata for what's on the dashboard, some overviews, citations, some helpful links. So right now this is only on this dashboard, but we will be rolling that out on all of our dashboards over the coming months. We also have this light dark toggle mode. The main goal here was just if you want to put this information into a report, that black background doesn't always look so good. So one thing you can do is if you come up to this top corner, there's a download PNG button, which is just an easy way to get this plot into a figure that you can then add into your presentation or report. Now, another dashboard that you might be familiar with, we have our supplemental snow measurements in this dashboard. So if you went out and took a measurement in association with an ASO flight, that will plot on this dashboard if you entered it into the snow data web portal. We're also plotting pillow controls on here in the diamonds, but you can turn those off if you like. If you hover over any individual point, you can get when the sample was taken, where it was taken, the SWE, the height of snow, and the agency that took it. And if you want even more information, if you go to the dashboards tab, there's a little drop down over here that'll bring you to a download option that brings you to a CSV, which has all of that information, but it also has any notes that were taken in association with that sample. Then this Bulletin 120 forecast verification, I'm not going to spend much time on this, but there's a lot of plots here. It was modeled after the CNRFC plots for verification. So there's a lot of different plots here just looking at error in different formats by basin. This ARSS flights and SWE estimates dashboard. So this is all information that's also on the snow product comparison dashboard. I think the main intent here is just to have a ASO B120 region specific plots that have all of that information for all basins in one place. So that is also available to you. And then lastly, I think this is the dashboard folks would be most familiar with, our longest standing dashboard. So we have made a few upgrades to this since the last year. So the first one I'll mention is that we've now added this average dashed line to plot from the beginning of the season on for each basin. You can also toggle on and off different traces here. And if you move to another basin, those traces will hold. I'll also just comment that pretty much all of these additions came out of feedback that we got from external users. Another addition here is that we have added since last year Lake Tahoe rise. And thanks to Scott, we were recently able to add the observed daily Lake Tahoe rise to plot here. And then the last addition that I'll mention is that we've also added, in cases where the NRCS forecasts overlap with our Bulletin 120 forecasts, we've added the NRCS forecasts. So for those east side basins, these purple points here are the NRCS forecasts. So that's it for recent upgrades, but two things I'll note for upcoming upgrades. The first of which is you might have used a very mammoth CSV associated with this dashboard, and we will be splitting that into 2 CSVs. So any data associated with this top plot will be in one CSV, and any data associated with this bottom plot will be in a separate one. So hopefully that makes it a little easier to grab the data that you're interested in. And then the last thing I'll note is that we have plans to change the name of this dashboard because snow product comparison is a little more limited than actually what's showing up on this dashboard. So right now our front running name is Water Supply Forecasting Resources Dashboard. But if you have any ideas for a better name, please let us know. The window is short because we want to make this change before we get into forecasting season, but we love ideas. And just an FYI that will presumably change the URL here. So if your link breaks, just go back to the website and grab a fresh one. So that's what I've got. And I guess one thing I wanted to say is I just want to thank everyone for the feedback that we have gotten so far. A lot of people reach out if anything looks funky on the dashboard or just with new ideas, and that's been just incredibly helpful to us. And so please keep doing that. And I'll pass it on to Devon.
Thank you, Lauren. So these next 2 dashboards I'm going to talk about are focusing on really how to utilize iSnowBow a little bit more. We've had some great presentations on what that model is. And we're in this position that we are paying all these brilliant minds in this room, online, elsewhere, to produce these products. How do we get them in a way that is useful to our cooperators and transmit that data? So SWE3D is not a new dashboard. This was live last year. The primary focus of SWE3D was to plot ASO SWE on topography, which it's just really fun, cool visuals to look at. So by default, the ASO flight data will still be what populates this dashboard when you open this dashboard. We have changed a little bit. So we took off some of the 2D analysis plots and have really made this a visualization tool. So the bulk is this 3D plot. One of the developments that we've changed to is right now we are plotting the CNRFC subbasins on the topography. So you can see how those delineate with the SWE as well. And then the new update that we are adding this year is a toggle for iSnowBow, which will have near real-time daily SWE outputs from the iSnowBow model. So right now, I just have mocked up data for the month of March for the American. This is all that is up here. This is still very much in draft, so there are a couple weird things, but just wanted to get this out there. This will be live this next water year. And just like SWE3D, I'm going to talk about another iSnowBow dashboard as well. Huge kudos to Mark and M3 Works, guys. We've been talking to them. We will be hopefully hosting their model results as well. So there will be a toggle between DWR's iSnowBow model and M3 Works iSnowBow model for this daily data and also for the next dashboard that I'm going to talk about. So there's the navigation that you can jump to a day. We are hopefully working on ways to speed this up a little bit. It is a lot of data to pan through, but you can jump next, previous day, or to a specific day. That is the bulk of the updates to SWE3D. This will also have the light mode, dark mode. You can pan around here and plot an image if you want to put something flashy in a report. This next dashboard, this is the big new one that we're rolling out this year. This was really born from listening to feedback and conversations in our weekly ARSS calls. What is the information people want to see? What is the cadence they want to see it at? And is there a way that we can get this to our cooperators in something that is useful and easy to look at? So at a high level, navigating around here, again, this is a draft. I just have a couple basins mocked up. This isn't everything. There's a drop-down list for the basin. You have the same calendar navigation here, the same previous next day, jumping through the data. This needs some TLC. There will be a play option that will take, I think it might be a 1 or 2 second delay, and it will just step through each day on its own. Right now, it wants to start in January 1st, and we don't have anything for January 1st. So the other time control on this plot is my little snowball time indicator. You can jump anywhere on this basin-wide SWE time series, and it will take you to that date. So this plot really is kind of the control. The cyan line is your total basin-wide SWE volume. These shaded hatches, I went back and forth with a lot of people and on what sub-basin delineations are the best and the most consistent across our whole domain. Because at DWR, our domain is the Southern Cascades all the way down to the Kern. So right now, these are the Huck 10 basins. The nice thing about Plotly is you can turn on and turn off, and you can look at each individual one. You can double click, turn everything back on, and your hover will tell you what sub-basin that is, the date, and what the SWE volume is. And then these vertical dashed lines are the ASO flight dates. I have this really zoomed out right now so it would all fit on one screen. So the dates are a little bit small, but these are the flight dates. And then the center top plot was one that went through a lot of iterations this year in our ARSS calls. It is the elevation banded SWE volumes and thermal states. So what you're looking at here, it's 100-foot increments. The red is the isothermal SWE volumes. The shaded colors are the cold SWE volume, so any non-zero cold content value. The SWE volume for that, and then they are shaded by the average cold content of that elevation band. And then this green line shows the previous day's total SWE volume. So it's really cool to look at on a big accumulation day. You can see the green line here and where throughout the watershed snow gains were made. It's also a really cool tool to look at, if I get this date right, for an ASO assimilation in our model. You can see after this flight was assimilated, it actually removed a lot of volume, and you can see where elevationally distributed in the watershed that has occurred. These two right plots are similar. They're pretty much mocked up out of ASO reports or M3 Works reports. This is the SWE volume by aspect and elevation. And then this bottom right is the daily change in SWE volume and aspect and elevation. So the differences that you're looking in this elevation banded, this shows where that snow was potentially redistributed or removed or added by aspect and elevation. And then this bottom left and center bottom plot are kind of new things to look at. The idea with these is to get people thinking about what might be driving the evolution of the snowpack. The daily basin mass budget is pretty straightforward. It takes and keep in mind, this is model land, this isn't reality. This is what iSnowBal is thinking is going on in this model. So you can see the accumulations of rain and snow. And then we also have surface water input, which it's terrestrial water input, but iSnowBal calls it SWI. So to keep it consistent, that's what I have on here. And that is the combination of rain and snowmelt. So positives are adding to the snowpack. Negatives are things leaving the snowpack. There's also a term for the snowpack atmospheric losses, which includes things like sublimation. It is a much smaller order of magnitude in iSnowBal compared to these other terms, so you don't really see it showing up too much on these plots. The daily basin energy budget, this is looking at the sensible heat flux, net radiation, latent heat flux, and soil heat flux. And one thing is, I'm sure if anybody has looked at a lot of energy budgets, these numbers are a little wonky. What the model outputs is a watt per meter squared value per grid cell. All of our models run on a 50-meter grid. This is just all of that summed over the snow-covered area. So the magnitude doesn't mean a whole lot. The cool thing to look at here is kind of the relationships between the different energy budget terms. And I will say, I know people are pretty sneaky. This URL is not live. You cannot access this right now. But we will have it live hopefully soon. This is still in drafts, still in iterations, working through all the kinks that come with all these fun data visualizations. Yeah. So that is our new developments. Like everybody on my team has said, feedback is greatly appreciated. all of this work has been born out of what our cooperators need, the conversations that we have with them, and how we can best get that information. So if you want to visit our website, QR code on the left will take you there. And then this feedback form is just a very simple name, email, open entry feedback box. So that is all I have for SnowTrax.
Thank you. In the words of a famous Vulcan, fascinating. Thomas. Yes.
So I do have a loud voice. All right, awesome. That's fantastic. I love to see that. And what's one thing I really want to point out, going back to the physically based and spatially explicit modeling, is much of this is entirely inaccessible unless we have those kinds of models, and that gives us that aspect into the deeper understanding of what's going on in the basin. So that DWR is adopting this and carrying it to new places is really, really cool. So thanks for what you guys are doing. I have a question. Where do we stand on formalizing the requirements for, and this is really a question for you guys, in particular for you and us, in formalizing the definitions for supplementary measurements?
Like like a protocol for collecting supplemental measures?
Because I know in the middle of the season, you were hoping for them and we were talking about it a little bit, but I don't remember that we ever really got there.
Yeah, I hate to put you on the spot, but
Please.
I never received anything from you guys about what your measurement protocol was.
I remember saying it in the meeting twice, but
in that direction.
But we need, so that's why I'm asking. And so I want to make sure that we do that.
Yeah. So Jacob mentioned our co-op meeting this fall. I don't know if you guys are familiar, but there is a snow survey manual, a snow course manual that we publish. There will be a supplemental measurement section, I guess, that we're adding to it. And then there will also be a snow course control. So for people who haven't measured our course or our sensor controls, there's kind of these really old grandfathered maps that only portions of them exist. So we're trying to standardize that protocol as well. So I'm hoping that by that, our meeting in November, we'll have a draft, hopefully with your input.
Okay. Yeah, no, now that we're not in season, that's much easier. The final thing is with respect to the name for the overall dashboards. My recommendation is that you pick the acronym you want and then build it from there.
Jacob is the king of acronyms. I know, and we couldn't figure out what to make FIGHT stand for. Oh, it's not up there anymore. Yeah.
In NASA.
Factors in time evolution of snowpack.
NASA has formal training on this, right? Yeah, I mean, you guys have to go through hours of training on acronyms. Let's see, we do have a couple minutes if anybody else has a question for the team. No, everybody's just frustrated. They couldn't get on the site that you were demonstrating at the time.
Oh, Matt tried to sneak on it in our last meeting.
Sure.
That's why I said that.
All right. Well, thanks, guys. Appreciate it. That was awesome. We look forward to it this year. And we're going to do another piece of hardware checkout switch. What's that? Oh, yeah. While Molly does that, let's see. We've got Mark Robertson here. So everybody knows Mark from In3Works. And I think you're going to be talking about all the amazing updates for the coming year, fixing everything that's been brought up already at the conference.
Don't start it like that. I can't. I'm already behind. I realized Amy and Michelle did such a good job describing ice snowball. I think I have some slides I can just skip. That's the plan. Awesome. Yeah, thanks everybody. So part of actually what occurred to me, I am honestly going to skip some slides or go really fast. Also to catch up time, but I thought it would be cool just to throw out there I'm going to be fuzzy for a second. I love working with everybody here. It's such a neat community. It's the same thing at the California Cooperators meeting, and certainly the work that we do. Is the sound okay? Not too okay. What's that? Closer? Is that better? You know, the work that we do is only possible because of all these other groups, DWR, you know, NRCS, obviously everything that ASO does. So yeah, big thanks. And now I don't know how, okay, arrows, cool. Yeah. So I'm going to talk, this is going to be a little bit hand wavy. This is things that are in progress. These are what we've been doing the last couple of falls, tell folks what we've been working on. We don't have finished results yet. So maybe we'll do that at the cooperators meeting. I don't know. Be a little hand wavy, but I'm going to talk about 2 new modules we have and then a quick look back at water year 24. So M3 works. Most of you are somewhat familiar, not going to linger. Myself, Micah Johnson, Kahan Yang, and Micah Sandusky, also known as Prime. We're going to skip this because they did a good job. The only point I'll make is that Ice Snowbell, the reason why we are part of the ASO family is it was designed with the idea even back as early, I guess, as 1999, that remote sensing products were going to be a thing. So replacing model variables, snowpack state variables with measurements is pretty straightforward. So that's why Tom, or part of the reason why Tom approached Danny Marks originally. Back in the day, gonna skip. 50 meters, great, cool, boom. Okay. Another sort of neat transition that's happened in the last couple of years is we're changing the way we're thinking about modeling. So, you know, interesting overlap with what was talked about earlier as well, what Adrian had. But viewing Ice Snowbell less as a standalone thing and more as a connection, a time series connection of remote sensing measurements. We have so many ASO surveys now. We have ASO Albedo. The scope of modeling is getting narrowed into the pieces in between, which is where it belongs. There is, like Adrian mentioned, there's a lot of uncertainty in models. We can constrain that with measurements. So it's a little shift in the thinking that's going on. Can skip this too. These are the ASO program with some liberties with geography here in Oregon and Utah. It's okay. So jumping into some of the new developments we're working on. Again, this will be hand wavy. Wind redistribution. We're really excited about this. The figure here needs a little explanation. This is Moores Creek sub-basin of the Boise River Basin. The colors here, this is 3-meter LiDAR. This has been clipped to deep snow. This is a midwinter day, but we're only showing snow that's 2 meters deep and deeper. The blue is the model values. The takeaway here, we all know, and Eli talked about, right, wind redistribution is complex. The point of this graphic is just to show that we are beginning to be able to line up model drifts somewhat with measured drifts. So who cares, right? I mean, we don't need the snow distribution because we have ASO. That's true, but our purpose within ASO is to get good density fields. And if ASO flies and we don't have deep snow in the places that are deep, we have bad density. And Kat will look at me angrily and we'll exchange bitter messages. And honestly, that's another segue. Tom had a mission statement. We have a mission statement at M3 too, and that's keep Kat happy. So that's why we care about wind. This is Senator Beck. This is an ASO survey from 2017, I think. We're doing just real small scale iterations now. We'll move up to spatial soon. This is a new wind model. It retains the Winstrel methodology, if you're familiar with that. There are several hideous bugs in the existing ARS code. So it's built off that in a way, but it is also at the same time new. The Winstrel methodology is baked in. We're doing an entirely new parameterization of the scour and the drifting that's based in large part, obviously, on ASO measurements for all these basins that we have them. So that's wind. Hopefully we'll have this up and running for water year 25. That's the goal. Next up, we've got a new albedo decay. function. So the out-of-the-box ice snowbell albedo methodology is good, but it just does not put enough energy into the snowpack. We've heard this talked about too. So we've had a Band-Aid for many years now where we just slap on top of the model albedo, we slap a date-based additional decay, which is a terrible way to run operations because you need knowledge of what's happening in the future. So we do okay on guessing those parameters, but it requires reruns. We'd love to move away from that, and that's what we're doing. This is work that Kahan Yang is doing. I'm not going to go too much detail on those slides. Apologies for the small labels here, but drawing your attention to the bottom two subplots, and it'll be the same on the next slide as well. Green are measurements at 5 energy balance stations. So the green lines here are measurements. Blue is the original model albedo parameterizations and then resulting solar radiation in and out. Orange is the new parameterization. So this one's net solar. Orange is a lot closer to green. That's the takeaway. Same with lower panel here, which is shortwave. Again, not going to linger too long. There's a lot here. This is Q's data taken daily at local noon. But again, what we're looking at is just where the orange values are a better representation of measured than the blue. You can see we still have some work to do for visible albedo, but near infrared is kind of spot on. So we are retaining the same grain size growth idea for handling albedo, but reparameterizing that. Another help with that is the ASO albedo measurements that we have. So that is that. That's the end of new features. Moving on to some discussion about model performance, also really interesting in the context of what Adrian had to say. So a quick look at Water Year summary from Water Year 24 summary from our perspective. We're real happy with the performance this year with our ice snowbell implementation. We did a lot fewer model reruns than we have in the past. That's because in large part, ASO vegetation height is now part of our package, been a huge improvement to the energetics. We did not have to do a whole lot of precipitation bias correction in California. That's really needed in Colorado. I just parrot what other people say because I'm not an atmospheric scientist, but you know, I think the general understanding of precipitation in Colorado, sort of the twin issues of convective storms are tough, as well as not great radar coverage. So precipitation bias correction is important in Colorado. Anyway, moving on. We didn't do a lot of that in California. Is it still? Yeah. Didn't do a lot of that in California and really stopped after January. There's just not enough high mountain precipitation sites in California that measure well once there's snow on the ground. So it's a limited approach there. But there's a caveat to doing model comparisons to ASO flights, or there has been in the past. Tip of the cap to Tom here. Tom and Kat sort of drove the first look at this work last year. This is a little schematic. I'm actually going to jump forward right here. The way that we used to say, how did the model perform in comparison to what the snow state actually was to take the last model output and compare it to the end result of ASO, which is a pretty crude way to do it. For a 2-day survey, you're rolling in 2 days of model physics into this comparison. I don't think it's that useful of a metric to operators beyond having a sense for how well the model does before we have updates. But it's also a very crude way to generate, how did we do? So before, again, we would compare the last model day with the end result from ASO. We were not saving off the model results in the survey. And if it's a 2-day survey, we don't save the day one original model values. It just gets overwritten with ASO depths. But we are saving those off now. It ended up being a little bit more complicated than we thought to do that, which is part of the reason we waited so long till Tom said, no more, you have to. Great, so how did we do? I did not put an R squared on any of these because it's a little disingenuous. I don't, for the reasons I just showed. This also rolls in some reruns. So we're not at the point where we can put a number on this, but this is what we'd like to do. Not as many flights in Colorado, a few outliers there. The ASO survey volumes on the X, model pre-survey on the Y. We can also do it with snow-covered area. And then lumping in California, we can do the same thing. There's a lot more flights. There are some outliers. I think that worst one, the yellow, was the third King's survey, I believe, where the model was pretty low. But overall, obviously, the model is performing just in a big picture, 23,000 foot sense, fairly well. There are enough surveys per basin in California that we can start to do sort of a mean error for each basin for each year, which I took a stab at here. The takeaway is that in general, not always, but in general, we're looking at single-digit % errors most of the time. And again, the point of this is measuring, if we don't get the mass right, we definitely aren't going to have the density right. And that's the goal, is to have the best density we can. So this is a useful sort of guide for us to be able to get as close as possible on that. Same thing with snow-covered area. This is a huge improvement from years past. Again, I mentioned this earlier, the model energetics have been much better parameterized since we included ASO vegetation height. The work that Amy's doing, and that has improved our snow-covered area in the past, really not melting snow down low. Lots of reasons for that. The work that Amy is doing too is going to help this even further, improving our vegetation parameterizations. Definitely a way to make immediate impact on model quality. So snow-covered area is typically less than 5% mean error per basin too. Going to skip these. Lauren and those folks talked about it. We have some new cold content figures, not worry too much about that. Skip this for the most part too. We still are working on a new density algorithm, or let's say new is not fair, refining the density algorithm. But we've talked to, internally with ASO and ourselves. That's the point of the exercise, density for combination with measured depth values. We really can't do a lot with density until we have the precipitation right, until we have the energetics right. Otherwise, we're going to over-parameterize density for the wrong reasons. So we're getting to the point where we can really dial in the density algorithm, but we're taking slow steps on purpose with that. And then some folks asked about this. This is just a little Mark tangent thoughts going here. We are going to start versioning iSnowBow. We've made enough changes to the open source code base that's available on USDA ARS that I think it benefits everybody, ourselves included, to sort of be specific about what version's being run, what features are included. So we don't have a final version yet. The print on here is small on purpose, kind of like Devon's link. Maybe don't read it too close, but the versions I think will be helpful in the future. Then lastly anyway, we've got some other projects we're really excited about too. So going to work with NRCS for historical modeling in ways that might be able to help operational water supply forecasting. DWR has funded an additional work to operationize, I'm making up words, to make operational our GFS forecasting. So we can do a 14, even 21-day snowpack forecast being driven by GFS. So they're funding some of that work in the San Joaquin. Again, working with Amy and Nick at Northumbria to improve vegetation parameterization, and then working with Hetchatchee folks to update and recalibrate PRMS. So I think that's it. Yeah, that is it.
Awesome. Anybody else?
Intercepting you for the online question. Yeah, I'll get you after.
I didn't. They took it away, Tom, not me.
Thanks, Mark. We got a question online from Carl Wetlaufer, and he says, do the in situ energy balance stations Mark reference just measure shortwave incoming / reflected albedo or long wave as well?
Wait, do they measure long wave as well?
Yeah. Or is it just shortwave?
Some do, and I don't know off the top of my head which ones. I assume Q's does, right? Long wave. Anybody know in the room? Q's does that have long wave? Kahan would know. I do not. I'd have to pass on that. Everything.
Hughes has incoming long wave and then surface temp.
Okay.
Incoming long wave and surface temp. So one thing that I just wanted to point out that we talk about quite a bit is you guys are you're converging really well on the mass for as we get to those updates. Remaining though, and you guys are aware of this, but just for everybody else, where that is in the basin is still getting substantially updated. So the spatial distribution is still has a significant update from the surveys.
Oh yeah, and we will never ever get wind right. I mean, even if we're never going to get precip right, we're never going to get wind right. It's not a standalone product in terms of accuracy that's required in the basins that we're talking about. So yeah, the spatial distribution is not going to be captured by what we're doing. We're searching for ways to get better density.
Right. So we still need the surveys, but yeah.
Let's do one more because we are starting to bleed over a bit.
Thanks. I was just wondering, I don't really know quite how to pose this question, but I was wondering if you could just speak to kind of the potential self-referential aspect of comparing the ice snowball volume, like mass volume, when the ice snowball density is not used directly, but is involved in the ASO density. Like I was wondering, like in our Wyoming survey, we're doing some entirely fieldwork based density maps. I was wondering if you could like approximate a density field without without ice snowball and see, if like, is there a way of comparing the volumes from ice snowball to something purely data driven without that kind of like, it's right because it was used to create the thing it's validated against?
It's a little circular.
Yeah.
It's a little circular. Yeah. Next question.
Fair enough.
No, that's totally fair. I like being flippant, but that's totally fair. I'd love to talk to you offline for ideas. I think our end, and we do a root mean squared on depth, that sort of internal metric, which is not really intuitive if you're going to show that. What does that mean on a basin scale? Like, I don't know, but we could show improvement. I think the reason we haven't chased it too hard, it's more of an internal thing at this point, is it's more of a science question. So having some slop and like, how did we do? I don't think the operators, beyond having a general sense, they're not compared about 0.1% or something like that.
Yeah, and once you have one LiDAR survey in there, then the densities are going to evolve much better because you have the depths and et cetera.
Yeah. But great question. Thank you. Yeah.
Awesome. Our final speaker, Olivia's coming up.
All right, perfect. Thank you. So as was mentioned, my name is Olivia Kramer. I am a utility analyst hydrologist for the Turlock Irrigation District. And I'm going to kind of bring things back a little bit, bringing in some of the reservoir operator perspective as well, mixed with, the other hat I have to wear as being a hydrologic modeler. So we're going to be talking about the model refinements that we do utilizing ASO data. Now, most of you are pretty comfortable with the Tuolumne watershed. It's spoken about a lot when we're discussing ASO, but for those that are new, Turlock Irrigation District is a water and power utility located in Central California. And we operate Don Pedro Reservoir on behalf of Modesto Irrigation District and ourselves, who both co-own Don Pedro, which is a 2.03 million acre foot reservoir. What is unique about Don Pedro is it is not a part of the state and federal projects. It is a community-owned project. And what Don Pedro means for us, it provides our area with hydroelectric power, irrigation supplies, M&I water, as well as environmental flows. So now moving into our model. So we utilize a model called HFAM. And we brought this in right after 1997 floods. It was realized that we don't maybe have as great of a handle on what's happening in the watershed at any given time, and that we needed to better capture that. So what's unique about HFAM, it is on a hourly time step, physically based hydrologic model. Looking at, we can go from the state of the watershed at any point within the observed record. And then from that, we're able to apply things like forecast data from the GFS, as well as we can take 92 years of hourly meteorological data and apply it to that current state of the model to then create ensemble forecasts. Now moving into how does this relate to ASO? In this graphic, I am showing the modeled SWE from HFAM for this year, and then all of the ASO measurements that were done. Now, I want to note that this is done after we have made some improvements to the model based on ASO measurements. And most specifically, and what we'll talk about later, is that May flight is where we saw the greatest change. So in the beginning of the water year, a lot of our decision focus is on volume. You're looking at April through July forecasts, and we're trying to make decisions as far as what water is available to our farmers for irrigation, what is our FERC schedule going to be for environmental flows, do we need to make any kind of pre-flood control releases? Is there more snowpack up there than we can hold? Why wait to release it? Let's go ahead and release it ahead of time. And then we also have the energy resource planning component because we are an electric utility. So we're providing what we call the upstairs people, all of our power side are upstairs, with forecasts of here's how much water is available to put through the units. And they have to see, okay, are we covered enough to be able to support the grid throughout that summer period, or do we need to go out and buy gas or other resources? Then as we move past that snow peak, what we're really focused on now is the rate of runoff, because we need to decide when and how high is that reservoir going to get and be able to communicate that, because that affects how much carryover are we going to have going into the next season. It also impacts on irrigation demand. Our demand can change on a daily basis. And so knowing, is that water that's coming in for the month of June, is it all coming towards the beginning of the month, or is it going to be spread out throughout the month? And then we have to decide on river ramp rates. We can't just take, hey, we have this amount of volume that we need to move, and we have X amount of days, and just say, okay, we'll target the river at 2000 CFS. We also have to have a process of, we have to bring that down slowly for the purposes of environmental flows so we don't strand any fish. And so that has a certain amount of water associated with it and a certain amount of time in order to do that. And then finally, on the hydropower end, you then have day-to-day demand. So that's where that rate has an impact on the day-to-day summer demands. So how are we utilizing ASO data within the model? Now, when we first started getting ASO data, these were the two methods that most people use. So mass balance adjustments, that would be kind of using the grammar plot, or you would look at ASO, look at HFAM output, and then if ASO was 50,000 acre feet higher, do a little bit of back of the envelope and adjust your overall seasonal volumes coming out of HFAM to kind of adjust for that difference in the initial condition. And then the other component is then the direct assimilation. So this is just taking an ASO flight and plopping it right into the model as a new initial condition. Now, these two methods are great when you need an answer right away, but it doesn't actually solve any issues in the long term. You're not making any improvements to the model of why the model wasn't producing the values that it should. And I think this is something that Scott had mentioned about direct assimilation and the issues that, CNFRC has had placing that, because you aren't impacting any of the other parameters and variables that potentially you put too much water in the soil moisture. And if you aren't moving that water, if you're shifting it to the snowpack, you're going to have issues later on, especially with that melt rate. So the part that takes a little bit longer, and this is more coming from the modeler side of it, of, okay, model was off, we need to fix these things. So one of it is you can use ASO data as a way to QA/QC your input data. This was really important to us last year in 2023 when most of our stations either weren't working or were buried in snow. So the temperature readings we were getting was the temperature of the snowpack. It was not actually the air temperatures. And so it was really important to us having that information and that feedback from the system. And then the other component, and these are getting more into the actual calibration of the model, is parameter refinement as well as station assignment. So not ASO, HFAM has, those 700 segments throughout the watershed, and we only have a couple of stations, and so we have to apply those stations to those land segments, and they all have their unique relationships. Well, as we move on, we get new stations, as well as we start to realize, okay, maybe that station isn't as representative for that land segment, and we can reassign that. So the way in which we make that decision, so what I want to dive into is, as a reservoir operator, I would look at the flight from April 2nd and see ASO 992,000 acre feet, HFAM 991,000 acre feet, less than 1% difference. Why do I need to even look into this data? Seems to be no issues. Well, what we want to see is there any bias, right? That's an overall volume. And what we know is for the rate component, that spatial distribution is vital. So this is then taking a look at what is that spatial distribution difference between the model. And so in this, we're seeing lower elevations. HFAM was producing higher SWE, and then it had lower SWE in those upper elevations. And as we move through, we want to also look at the components that make up that SWE. So this is taking that same flight and just looking at the depth differences. And what's interesting is that there is an overall bias here where HFAM has has higher depths than what you're seeing coming out of ASO. And then on the opposite side of it is for the densities, it has a much lower density than what's being produced by M3 Works. So this is kind of something that we want to look further into on past flights of, is this typical? Is this common that we're always biased on the depths and the densities? Or is it just happened to be this year we were seeing that type of relationship? And just to give a little idea of, here are real impacts to it. So as I mentioned, 2023, we used it a lot for input data QA/QC, but it was a year in which we also did some station reassignment. So this was the original station assignments. Each color represents one of those stations within the watershed. And this was the change in which we made, where we did some reassignments. We had some new stations that we could utilize. And we ended up be able to better capture lapse rate within the watershed, and we improved the overall historical calibration. So that's the other component. You can't just perfectly fit it to that single year. You also want to make sure whatever those calibration changes have impacts on your historical data set. And then finally, I want to go into 2024. As I mentioned, the May flight this year was really important to us. As we were going through the year, we noticed as we entered the melt period, blue represents the observed data. Observed is on a daily full natural flow. And then the red is the simulated HFAM values for full natural flow, which are hourly. So just want to know why the shaping is a little bit different. But you might notice we weren't melting enough, or we just knew at least the observed and the simulated weren't matching. in that early period. And then we were carrying a lot of snowpack towards the end. Now, in that time frame, we knew we had an issue, but there was that question, you know, between that April flight and May flight, there was precipitation going on. So were we not capturing enough precipitation and that was leading to those higher observed flows, or were we not melting enough snowpack? So there was that question sitting there of, you know, what is happening in the system? And unfortunately, the snow sensors aren't detailed enough for us to actually look at that on a monthly basis. Is that how different are those rates coming down? So once we got that ASO flight, we noticed HFAM had about 60,000 acre feet more SWE in it for May 2nd. And with that, we were like, okay, so clearly it is that snow melt issue that we're dealing with. So we started to play around with some of the parameters, and we were looking at parameters that impacted that melt rate. And with those adjustments, we saw one, improvements for our results for actual 2024 full natural flow, but also just within the long-term record as well. And that's where that previous graph you saw, why we had such great fit for all of the flights to the HFAM outputs for SWE. And finally, I kind of want to just mention some future work. As I mentioned, we really do want to look into, we have a long record within the Tuolumne, looking at some of those long-term model and station biases. Can we overlay our station assignments on the ASO differences graph, identify specific stations that are causing potentially higher values in, you know, lower elevations versus upper elevations, and then even on the ideas of as far as density and depth and what that relationship is on the long term. And then I think the other component is a lot of our collection is in the accumulation period and at the peak. You don't typically get a lot of collection in that runoff period. It's only in those wet years that we've said, oh, we need late season flights only in wet years. I think from a modeling standpoint, it would be important to get a couple more data points in that spring runoff period. We've found within our model, it does a really good job. If it has the right input data in the accumulation period, it does a great job at capturing accumulation. But as far as on calibration, it's a lot more in that melt period. It's really sensitive in that melt period. So I think capturing more data in that would allow us to kind of refine those parameters. And then, you know, below is just kind of the overall calibration of the model from 1931 to present, and how can we continue to improve that. So with that, I'll take any questions.
Certainly feel your pain on the calibrating the melt side of the equation. It is challenging, especially when you have active weather. Yes.
It's fascinating how you're calling for that and what we've seen. So in the first 3 years of ASO, our first flight in the year would be around peak, and then we were hitting the ablation period. And since then, operationally, there's been more call for coming earlier in the year, but what it's really saying, Ramesh, is we need a longer program, right, Wes? And so this is where the community needs to come into play with respect to pressure for funding so that we get everything that we need.
Cool. Joe.
Thank you. And I mean, I was blown away already by the beautiful volume versus rate. I mean, that was so nice and clear, but it was really exciting to hear you talking about solving for the areas of influence of your stations. And boy, that's a beautiful optimization model with your 90 years of history. Have you cast it that way? Like solve for, say, solve for the correct influence areas for every station given your 100 years of data. That I know you said you kind of did it, but I don't know how you formalized that.
Yeah, and I want to make sure I'm following what you're looking at. So you're meaning as far as when we're trying to find assignment for stations?
Right, and actually draw those polygons from your history to make them most efficacious, right?
An evolutionary optimization kind of thing, I think.
Or I have no idea what kind of optimization it would be, but you know, anyway, I think that's that's a cool opportunity there with that history.
No, definitely. I think that's something we can look at.
Awesome.
Mm-hmm. No, and I think with the change component, that is something that led to some of the calibration we did this year. We increased the convective melt, and that was what helped with some of that runoff rate. And the reason for that is we didn't really see the need to do it in previous years, but what we've noticed is minimum temperatures keep going up, especially in that May period. And the model wasn't sensitive enough to now those increases we're seeing in minimum temperatures due to climate change. In the history, it didn't really matter because you didn't have those high minimum temperatures. So it melted off fine. You didn't need to have those increases in the convective melt. But now we're seeing the impacts of climate change and how you need to fiddle with those parameters.
Awesome. All right. Thank you very much. One more round. We will reconvene at 1:15. So yeah, get out there.
Be our last session of the week. So yeah.
Yeah. Molly's rocking. Molly, do you want to get Cody set up, or do we have to switch over for his?
Hey, Dave,
Okay.
Cody, can you hear me?
All right. We have Cody Mosier queued up from the CBRFC to talk about how they've been using ASO data in their experimental forecasts.
All right, thanks. Good afternoon. I'm Cody Mosier. I'm a hydrologist, operational forecaster at the Colorado Basin River Forecast Center. Been at CBRC about 7 years now, with about 5 years of additional forecasting experience on the East Coast and the Pacific Northwest. So today we're going to take a look at some of CBRFC's experimental forecasts using ASO data with a focus on this past water year. So just a real brief intro on what we do, what kind of forecast products that we produce. So it's anything from 10-day, these are short-term, hourly, real-time forecasts. The map on the left there are a bunch of points. These include real-time reservoir operations. We provide year-round decision support, anything from high flows and emergency response with flooding to low flows, July through October-ish, and everything in between. So year-round decision support, as well as water supply. So our water supply forecast points shown in the middle graphic there. And that's, I think most of us know, for longer-term water use planning and management. And then we also provide some spring peak flow forecasts shown, the points on the map on the right. These provide the threat of spring flooding due to snowmelt. So we do this, we have a hydrologic modeling framework where we simulate soil moisture, snow accumulation and melt, reservoir inflow, outflow, pool elevation, fill spill type stuff, routing, irrigation demand and return flows, as well as some real-time assumptions about unmeasured losses and gains that are out there. So here we're looking at the 2024 ASO flights over our forecast domain during the 2024 water year. There were a total of 16 flights this season. A lot of these have been talked about in the last few days. There was an upper green flight that, from my understanding, it's just a snow depth product out there, but maybe there's a sweet grid out there that we could use. So in total, we produced 44 experimental water supply forecasts during this past water year. So our forecast domain shown on that center graphic, so it's the Eastern Great Basin, Upper Colorado, Lower Colorado, that we're covering with our forecasts. And then zoom in on the right, you can see this is basically looking at the Upper Colorado with the blue shaded areas. Those are ASO SWE grids from April flights. So it gives you an idea of coverage with flights in our forecast domain. So the way that we're using ASO data in our modeling to produce these experimental forecasts, so we're taking that 50-meter gridded ASO SWE product and we're computing a mean aerial SWE for catchments in our hydrologic model that the ASO flight spanned. And then we're running our ESP model with that ASO SWE. It's an offline version of our model. And this output from ESP is 30 hydrographs with the ASO snow states. And then in the future, we're using 1991 through 2020 observed weather. So those 30 future hydrographs, you can take those, you can produce a probabilistic water supply forecast. Or you could take, the 10 driest traces or whatever traces you want to look at to come up with some sort of probabilistic water supply forecast. And then the graphic on the right here, this is what the final experimental forecast product looks like. It's a one-pager showing the location of the forecast, the flight of the ASO date, a blurb about what the product is, a graphic in the middle showing how the water supply season has evolved, typically since about mid-December. It's got our daily ESP guidance on there, our first of month official forecast, and then it's got this experimental blue forecast that uses the ASO SWE data in our model, and then a table on the bottom showing various forecast volumes at different probabilities, with the ESP 50 being the median forecast. So in this case, our experimental forecast for this flight at this location, 56,000 acre feet, whereas our ESP model guidance using our operational snow states was 4,000 acre feet lower at 52 CAF. So that's how we are bringing the data into our model and producing our experimental forecasts. Here we're just looking at some other ways that we're looking at the data. This is an example from the Gunnison River Basin this past water year above Taylor Park Reservoir. So the graphic on the left, this is looking at our model sub-basin. So in this case, we have two modeled basins. Each of them have two elevation zones, with the upper zones being above 11,000 feet and the lower zones being below 11,000 feet. And then the table in the upper right, this is an analysis or comparison of the volume of SWE and the water supply forecast. This was from the May 20th ASO flight. So in this example, ASO reporting 111,000 acre feet of SWE, whereas our model had 120,000 acre feet, 8% difference. And then you can see how that translates into the water supply forecast, gives you a little bit of sense of the sensitivity here. And then the product or the graphic on the lower right. So this is an end of season graphic, no numbers on it, but basically what these graphics have is this observed volume line that starts April 1st, ends at the end of the forecast season, which is July 31st. And at the end of the season, we have an observation. And at this point, these are provisional observations. I don't think the USGS has quite officially approved all of their observations for the past couple months. So I would expect some changes in these observations, but probably not much. We'll see. So in this case, this red arrow is basically just showing you on May 20th, our ESP guidance, this black solid line would be the ESP 50, throw an ASO into our ESP model and running it results in a lower forecast due to lower snowpack. More ways we're looking at the data. When it comes to our forecast operations, just making pretty basic, simple scatter plots with certain thresholds, just looking at comparing Snow 17 versus ASO SWE. So we're looking at everything, all flights during the water year 2024 season, the number of cases, a correlation value, throw it on a scatter plot. So anything above the solid 1-to-1 line would be Snow 17 higher, whereas below would be SWE, where ASO is higher. So this is all zones for this past water year. We're also looking at it based on a elevation threshold. So in the upper right here, for example, everything above 10,000 feet, there were 100 cases of those. And then by basin or sub area, so the lower right showing the Yampa scatter plot SWE comparison for this past water year. So just ways we're looking at the data and comparing it with our operational snow states. Now these next couple slides are just a compilation of a lot of the experimental forecasts that we produced this year. Some of these have a comment in the upper left I thought would be worth mentioning or looking into later. So starting in the upper left, this is the Dolores River Basin. You can see this first ASO flight and second flight reporting lower SWE values. And the observed volume at the end of the season here, you can see came in much lower than at least the April forecast, much lower. I threw in the April through July precip. It was very dry in the Dolores, April, May, June, July. Precip around the 25th percentile. You know, so you can use that information when looking at these end of season graphics with verification. You know, it bodes pretty well with this dot here on that first ASO flight. You know, this would be the volume that would have a, you know, around a 75% chance of occurring, which would, you know, correspond roughly to a drier future. And in this case, it was quite dry during the April through July period. So that's an example from the Dolores. In the upper right, we're looking at the east at Almont. So the first ASO flight, again, early April, second flight, mid-May. So the first flight was lower, second flight right. Pretty good agreement with our model. And then the end of June got really wet. In this area, it was greater than the 85th percentile in June. And you can see, you know, that looking here on the evolution plot. So, you know, again, when it comes down to verification, that the future weather playing a role here, and the observed value coming in above basically all forecasts after May 1st. So there's an example from the Dolores. In the lower left, we're looking at Dillon Reservoir. This is in the Blue River. So I don't really have a comment on this one. The first flight, the snowpack from ASO was higher. In the second flight, it was lower, and verified quite well. And then the lower right, Yampa Steamboat Springs, kind of similar story here. First flight lower, second flight, nice agreement with pretty good verification. And then one more slide showing experimental forecasts. In the upper left, this is from the Roaring Fork. This area had severe dust on snow this past water runoff season. And then it is neighborly Gunnison and got wet at the end of June with the monsoon season precip ramping up. So 2 flights there, higher than our operational model SWE, and then, you know, verification kind of came in between the 2 forecasts there. I'm going to jump now to the lower left. This is Granby Reservoir. This would be that Windy Gap flight that Emily talked about yesterday from Northern Water. There were 3 flights here. All flights came in higher than our operational model SWE. Just commented there were, if you look between these 2 flights, there's 2 decent sized storms here, those 2 increases. So I think probably more time needs to be spent on, looking at how much SWE did ASO accumulate, how much did our model accumulate. Maybe there's something there that can tell us more of the picture about this particular area and forecast. Now in the upper right, this is Current Creek Reservoir. This is part of the Uinta Headwaters flight. There's 1 snowtel in this basin. All 3 flights came in lower than our operational model. They verified well. We removed SWE. You can see this drop here in our model. We removed SWE at that point in the season. There's 1 snowtel in this basin. So that was Current Creek. In the lower right, it's that same Uinta Headwaters ASO flight. There were 3 of them. In this case, the first 2 flights came in much higher than our ESP guidance at the time. The 3rd flight here came in really close with our model SWE. So that one's a bit unsettling. I think we need to look closely at what was, say, the NRCS or WRF Hydro forecasting for these first 2 dates here to, I think that would help us understand these 2 flights and data points. Now, a bit about water supply forecast verification. So this is looking at the last 3 water years. How many forecasts or I guess experimental forecasts did we produce? It's looking at just some very basic air stats. The table in the upper left is just a median absolute forecast error for all forecasts during the season. So 2022, about 9.5%. 2023, about 3.5% among both SWE data sets. And then 2024, we had about 3 times as many forecasts this past year than we had the previous 2 years, with errors, around 9 or 10% as a whole. And then upper right table is just the total forecast error. So basically, you take all the forecasts, add up the errors, and between each data set. So again, not surprising, you make more forecasts, you're likely going to have higher errors. It's pretty comparable, numbers there. Not going to get too much into those. And then the scatter plots for all flights and all zones across the bottom there for water year 22, 23, and 24. So more flights each year since 2022, more experimental forecasts produced, especially this past water year. A bit more about verification. This is focused on this past water year, the same 2 tables, upper left, upper right. This is just looking at, again, all of the 44 experimental forecasts that we made. It's showing the observation and then each of the forecasts with, say, Snow 17, SWE state, and ASO SWE state. You go from early season flights to late season flights. You need to have some knowledge of our basin IDs here. So not going to get too into the weeds. Probably the best way to look at this graph, if you're interested later, is to, find your basin or point of interest, and then, pick out a black dot. So for example, GBYC2, that's Lake Granby, you're going to have the same black dot. In this case, there's 3 flights. ASO is in blue. First 2 flights verified better. Second, or the last one did not. Another example, ALEC2, this is in East Almont in the Gunnison. So the observed volume was around 200,000 acre feet. 2 black dots here. So 2 flights, and then you can see how each of the forecasts, where they came in with respect to the observation there. So just a couple different ways, fairly basic ways that we've been starting to look at verification. Something new this past season is we started posting these experimental forecasts on the web after getting quite a few requests for them, and just making them accessible. So if you're on our webpage, cbrfc.noaa.gov, you can drop the water supply menu down and they're under the special forecast products page, or a direct link would be here. There's a link, for each experimental forecast, just that one pager. And then I anticipate, just needing to change that to 2025 for this next season, and it'll get you there. So a summary and some future work that we're planning on doing. So our goals here, just, transparency on how we're using the data, becoming more familiar with the data each year, and model development. Certainly, always seeking to improve model inputs and recognize the value of this data. Great reality check as an operational forecaster. Another tool we've integrated into our forecast operations and storing now to our operational database, and then development and transition into higher resolution snow modeling. This would be, related to a bit about what Michelle talked about this morning with NOAA Next Gen Water Model, and then always, just continue grinding away with verification and evaluation, looking at model performance. We plan on continuing to produce these experimental forecasts. Yeah, that's some of the future work that is ongoing. And yeah, that's basically what I had today. Just want to thank the ASO team for hosting this workshop. It's great to be there in person last year, but wasn't able to get away from the office this season. So thanks, ASO team. And yeah, we'll open it up for any questions, and you can reach out to me via email there.
Great. Thanks a lot, Cody. I'm sure we've got a couple questions here. I'm going to kick off the questions, a little prerogative. And just, it's sort of a qualitative question. You've got your experimental forecast where you're actually ingesting the ASO data into it. Is there any kind of estimate about how often you may adjust just your regular operational forecast just with the knowledge of about what that snowpack is versus what the background analysis is saying at that time? Does that happen a lot, a little, half an amount of time, or anything like that?
I would say probably less than half at this point. We're certainly, the outliers where we're off. The more that we're off, the closer that we're looking at it, obviously, and the better chance there is for us to make a real-time SWE adjustment in our model. Yeah, I think, we're becoming more comfortable with looking at the data. It's just some of these cases, like, the strawberry one this year, it's obviously we wouldn't have benefited from that. So it's just understanding why that is. And then the third flight is boom, right? It's right there. So it's these things that happen, fairly rarely. But it just kind of gives us pause and just going with it all the time, every time. That answers.
Being a new basin for this year too.
Yeah, it is a new basin. First year it was flown, so it's certainly probably more pause there as well compared to a basin that's been flown for 5+ years.
Yeah. Okay, we got a couple other questions here. This is Tom Painter.
Hey, thanks for doing the presentation. Wish you were here. Right now we're still stuck in the place where you're ingesting ASO data, but running that through the nominal calibration machinery. And I guess looking at the scatter plots that you were showing before, which I think are one or two slides before this, of the basin. Yeah, there we go. So you can see generally that Snow 17 with ASO as truth, Snow 17 is modeling toward the truth. When you discretize this further, and we've done this together, if you break it out by basin and then elevation band, some of those have different relationships, so that deviate from the 1-to-1, and so when are we, obviously, and this is probably a great segue into Gus's talk, but when are we going to feel comfortable to start putting together individualized ASO specific calibrations? And I realize not soon enough with respect to how many years of data that you most feel comfortable with, but can we take some steps towards trying to get down that path?
Yeah, I think certainly as we've been a little low on resources and stuff the last couple of years, but we have many projects or multiple projects now where we're starting to look at not only ASO, but all the various other SWE data sets out there and bringing them into our model calibration. And then how much time do we spend on that versus some of this higher resolution snow modeling stuff? And it's always a balance there, Tom, with forward looking and getting to a better, higher resolution model that this data is meant to be ingested in versus our current model setup.
Okay, thanks again, Cody. We're going to have to move on. Really appreciate it. And we do have an open modeling discussion later. I don't know if you'd be able to hang around for that, but would love to have you if you can. Our next speaker here is Angus Gus Goodbody from the NRCS. I think we all know Gus. He's a tall man. And but that's right. Do you want to load this one up?
I'm going to start whilst he's loading that up and just say it's great to be here. I love interacting with the folks who are at this meeting, and I think a lot of the best parts of this meeting happen, in those types of conversations. Although I have to say the presentations this round have been really excellent, and I've appreciated them. Anyway, I wanted to thank Tom and ASO for hosting this event. I think it's a really valuable way to bring the community together and take on some of the issues that still exist and celebrate the advances that are being made. So just waiting for slides to come up. So I'm going to get started. I'm going to generally present on how we're trying to integrate spatial SWE products into our forecasting or R&D or product. I'm going to cover some other things as well, just because I have an opportunity and realize we got a lot of California in here. Some people may not be as well versed in what we do at the NRCS Snow Survey and Water Supply Forecasting Program. So I'm just going to spend a second giving a little background. So the map I'm showing here is a combination of both our SNOTEL network, which I think is probably what people are most familiar with our program. We have about 950 stations in mountainous areas across the Western US, serving 12 Western states. Primary original development for these stations was really to support our water supply forecasting program. So that's the other part of our program. We have about 600 forecast points. Those are represented in green on the map. The blue are the SNOTEL sites, so I've got them both together there. Obviously, it's a huge domain, really diverse domain as well, as far as hydroclimates, snow environments, et cetera. So it's a little different than, I know lot of focus on Colorado, and they have a big job too, but our domain is quite a bit larger than California DWR has to deal with. Just wanted to point that out. At any rate, the way we do our modeling, we basically have to create a unique model for each watershed, issue date, and target period that we're trying to produce a forecast for. So that results in a lot of models, basically. And I'm basically estimating that on a given year, we're producing about 5,000 independent forecasts across the domain. Generally, we're doing forecasts beginning of the month from January to June. There's variability depending where you are on that. But that gives you an idea of sort of the scope of our mission and service area. Just going to talk about some recent USDA NRCS investments. Gives you an idea, and then I'm going to go into a little more detail on each of these. First and foremost, we had a budget increase recently, a couple of years ago, and we put forward a plan to our agency to put a lot of that money into increasing staff in our organization. Now, for those of you that work in government, adding staff to an organizational chart is not the easiest thing to do, and it's really, it's been impressive. The leadership team, where I work at the Water and Climate Center, but also at our snow survey program across the states, to get this done was a Herculean effort. And we're still, I'm sure some of you noticed, we've been hiring at a pretty rapid pace the last year, and that's going to continue. At the end of the day, we're looking to increase our staff by about a third, which is significant. So we're going through a period of pretty unprecedented growth, I would say. And it's really exciting, and I think it's going to give us a lot of opportunities and increased capacity to take on, different projects, which can include, some of these R&D efforts or research to operation efforts. Other bullet point here is part of this budget increase was sort of tied with the idea that we would put more stations out on the landscape. So we're trying hard to do that. It's not an instantaneous effort to get new stations out there. It's a lot of work, a lot of planning, a lot of permitting. It's not just in our hands to go out and put stations in. And we're also trying to do it in a very deliberate way, looking at where we have gaps in the network, not just horizontal gaps, but vertical gaps. Are there opportunities for monitoring things in different ways than we've done in the past to try to address, new issues we're facing, whether that's climate, non-stationarity, or other issues. So looking at a bunch of different ways to do that. In addition to the new sites, we're also working on supplemental sensors. So adding new sensors to existing sites, adding new sensors to the new sites we put in. And I'll go into that a little bit deeper, but we've had what we call a super site initiative that's been going on for a few years now in our program, and we're also recently going through a little bit of a sensor R&D reorganization within our group. I'll talk about that a little bit more coming up. We've also just recently updated our water supply forecast modeling system. So I know there's been talk about it's hard to make certain changes, and I generally agree with that, but there's definitely an appetite for doing it. So we've demonstrated that we can make those kind of moves. Granted, we're still using more of machine learning, regression-based approach, but as far as an appetite for things that work and adopting that into operations, we're completely open to that. And I think something got pushed off the slide here, but the other new investment, which I'm really excited to announce, is we've recently awarded a contract to M3 Works to do some ice snowball modeling for us. We're looking to basically extend records back 30 years and see what we can tease out of that information. So back to the network design idea, we've been developing some tools that really are focused on helping us optimize the investments when we put new sites on the ground. So what information can we use to inform where we're going to put sites? Part of this includes validating what our existing sites represent or do not represent within a basin. And then also new schema for monitoring. So whether that's tighter, higher resolution transects to capture elevation differences over relatively short distances, or essentially, though, monitoring at higher resolution, targeting very specific gradients that we think are important for modeling. And not necessarily just our own internal modeling, but modeling that's used. Our data is really used broadly across the community, so we're always open to ideas for improving information that's needed there. Just wanted to mention one agreement we recently started with the Bureau of Reclamation and Ethan Gutman at NCAR. So this is definitely using ASO LiDAR data and trying to see how we can use this to support our network design efforts. So is there information we can pull from these high spatial resolution scenes that can actually then be actionable in terms of identifying where we have gaps in basins for certain modes of variability of snowpack, for instance. So Ethan's going to take a deep dive on that. I know he's already hired a postdoc to sort of start looking at that. Other components, and I've got the objectives listed here. So this idea of how stationary, are the spatial snow patterns or not. ASO gives us a view of this like we've never had before. So that's an interesting one to look at. And again, building out a workflow that we can use. So as these scenes become available in new places, we have a workflow we can incorporate directly into our planning. And finally, identifying this idea of, is there a spatial subset within a basin that could be modeled, or excuse me, that could be acquired through LiDAR that still gets us a lot more information than we currently have, that isn't necessarily flying entire basins. And our main drive in this direction is really, again, back to the domain that we have to cover, and this idea of how do we balance, cost and bring improvement to snowpack monitoring to a broader, diverse set of areas. Especially in the NRCS, we do focus a lot of our work with private landowners and underserved people in areas. So this is something we're very interested in exploring further. SuperSite initiative, I mentioned, I've got a list of the main sensors that we're been testing and are starting to roll out. Nothing too crazy there, but a lot of things that can get us closer to supporting more of the energy balance needs that we have in different types of modeling. I'd also highlight the snow temperature profiles. So we've been using beaded stream cables to monitor snowpack temperature, which can be super useful in that sort of cold content space and understanding the state of the snowpack and readiness to melt. And then I mentioned the reorganization. So really a lot of our R&D within our program historically has been driven from our state programs. And oftentimes, so we have 6 data collection offices, and they've often independently worked on just issues that are happening in their area. A new model we're going to is more of a program level approach, where we're going to put program level resources onto it and sort of work as an entire program to prioritize those efforts. I think at the end of the day, that's going to result in a lot more capacity for us to work and explore new sensors that can be useful and do it in a more systematic way. So the evaluation can really be useful for making choices about what's appropriate and what's not. So now I'm going to pivot into the new NRCS water supply forecasting system. So this is a result of a multi-year effort that we undertook initially with external contractors and then also a lot of internal work. But as we did this, we really started at the beginning, and we're thinking about, for what we need to do and the people we have on staff and the resources we have, what type of system fits what we need the best. And so we did go through sort of this look at, process simulation models versus machine learning versus classical regression. And the fact is, they all have pros and cons related to the resources required to do them, results, the probabilistic accuracies, all these things. And so in our case, we stuck with sort of this combination of classical regression and machine learning. And certainly that has to do with the resources we have to run certain types of model at scale for the domain that we have to cover. But anyway, there's some information there. I'm not going to go into too much detail. But if people do want to know more about the new system, M4 is what we call it. It's a multi-model machine learning meta system. There's 2 publications that are out there that have all the details of really the nuts and bolts of how the system runs. I will say that our adoption of the system that's represented in these papers it's pretty darn close. We continue to evolve certain aspects of the system, but this will really give you a good idea of what we're going after there. And then just key points about it. So this is a big change for us because we're actually running 6 independent models. So historically, we've used principal component regression, and oftentimes we'll just have a single model, and that's our guidance. Now we're running for each of those forecast points, publication dates, we're running 6 independent models. There's a list of some of the methods there. The new methods do give us some flexibility in addressing some of the more nonlinear problems that we encounter. Although honestly, a lot of our snowpack modeling issues really are fairly linear in nature in many cases. Still use a data dimensionality reduction step with principal component analysis. A couple of uncertainty estimation techniques, and that's definitely an area that we're still actively working on to improve. In our view, for these uncertain type predictions, we know that the correct representation of the exceedance probabilities, et cetera, are really the most important thing for our stakeholders. So needing to encompass all the levels of uncertainty that go into the forecast is important. And actually our methods here are quite good at doing that. Genetic algorithm, which is an automated feature selection piece. So running 6 models for all these points with basically the same size staff. We have increased our staff a little bit. We need automated steps to be able to do this at the scale that we run our models. So we're using some, basically we can put candidate predictor variables into the hopper. Genetic algorithm can pick through them and try to optimize for each of the individual models. And at the end of the day, we take those 6 different models and we wrap them into a single ensemble. So right now we're just using simple ensemble mean. So we're basically taking the 6 valid models and combining them, and that's effectively the forecast that we publish. Persephone is another word you'll hear associated with our new system. That's really our user interface that we use to actually interact, pick the stations we want to use, gather the data we need, format that data into the format that's needed, send that to, we've basically built a software as a service where M4 sits. So then the computing there can do that processing. Typical time for us to calibrate a single model with the new system is about 15 to 30 minutes. So we've also had to address how do we scale this type of processing for all the points that we have to manage. And we're working with an agreement through Colorado State University to kind of meet our computing needs and help us with solutions there. Yeah, and again, just creating workflows that make it easy for the analyst or the forecaster to actually get the job done. There's a lot of work and picking that has to happen. A lot of this is really about cataloging, organizing, saving that information, making it easily accessible. So a lot of that's accomplished with the Persephone interface. And so yeah, as far as Empower, what does this really do for us? So it's improved model management compared to our old system. So we're doing more models, but it's actually in many ways easier to make the choices that we need to make to build these models, which at the end of the day allows us potentially to do more frequent model recalibrations. Also opens the door for more frequent forecast issue dates. So that's something we're moving towards, away from the monthly, more towards the weekly, I would say, is probably where we're headed. And it frees up individual hydrologists' time to do more model interpretation and value-added stuff aside from just turning the crank. So the other thing it's empowered that we've been able to see is we've seen incremental improvement in forecast model skill just by going to these new methods and using the ensemble approach. And I'll demonstrate that in a second. And finally, this is sort of the platform. We see this as the entry point for us to now do more R&D, test new input variables, et cetera. So now we have this in place, we can kind of move to the next phase, which is to how do we use additional data that maybe right now is a vulnerability for our models. How do we actually bring that into the fold directly into our modeling? This is just a quick, this is my operational area from last year. So I did all the model building for the Upper Colorado, Rio Grande, and Great Basin. These are April 1 forecasts. These are just 3 different skill metrics. And all I'm showing here is our legacy system versus the new system. So it's not every point in the basin, but it was every major sort of node that I had modeled at that point. It's not cherry picked in any way. These were just what was done at the time. But basically, you know, R squared on the top. So the orange is for the new M4 system. The blue is essentially for our legacy system. It's actually what our published forecasts were. And you know, in this case, better R squared is good. In general, that's what we're seeing across the across most of the points there. Root mean square error in the middle, smaller is better. We're seeing improvement in the correct direction there. And then maybe the biggest change is in the maximum error from any given model. So there's a significant reduction in the maximum error that you'd expect, which of course is, again, is the direction we want to go. Additional benefits, I've mentioned the ensemble mean. I honestly can't believe how well this seems to work. It's sort of remarkable in a way. This is just one example on the side, but it's pretty typical that the ensemble mean from these 6 members matches, or in many cases exceeds, the skill of any individual model. So this is not a new lesson. I know we have a lot to learn from our meteorology and climate community on this, but it's definitely a really exciting part of our new system. And it also opens the door. When I think about how, as a community, do we work on these things, to me, diversity of modeling approaches is definitely a benefit, in my opinion. So rather than this idea, we need to create the one model that does it all and is the best, I think there's something to be said for this multi-model approach and ensemble approach. And having simple ways to combine different valid models can be a legitimate way forward as far as how do operators make decisions with regard to, hey, now I've got 7, 10 models to choose from. What do I actually do with that? I mean, there's a lot to be learned from looking at individual models and knowing how they perform, but there's also a lot that can't really be known. And in that moment of decision, it's often hard to know exactly which model is going to end up performing best at that time. So that's really exciting too. And yeah, as an example, we can talk about the river forecast centers with NOAA or the ASO Wharf Hydro as potential members of this greater ensemble that we could use. So just to get in, I mentioned the high resolution physical snowpack modeling contract with M3 Works. So what we're planning to do there is basically do daily model runs for the past 30 to 40 years for 15 test basins that we're going to select from a variety of hydroclimates across the West. Demonstrate the near real-time modeling capabilities, which honestly has already been demonstrated by M3 Works with the work with ASO. And then we want to test. So once we have that data in place, we want to test different schemes for extracting features from those data sets and feed them into our modeling system, essentially. And at the end of the day, if we see improvement, that's great. And those would be the types of things we would pursue for operational deployment. The other use we're thinking about is back to this network design bit. So ASO is pretty limited with the number of scenes we have right now. This is going to give us a lot more data over a longer period of time, so potentially can be revealing in terms of patterns of snow accumulation, et cetera. That can also be used in our network as part of our network design toolkit. Okay, last little bit. We don't have that many years of data, but my colleague Carl Wetlaufer, who is the current operational forecaster in Upper Colorado, has been tracking the WRF Hydro, CBRFC, and NRCS forecasts for the last basically 3 years is what we have. So we have different forecasts from the last 3 years. Here's a list of the basins that are included in this particular analysis. So it's 22 through 24. These are all April, May, and June forecasts. That's essentially, when the ASO flights are happening and when the WRF Hydro models are being run. April, July volume is the target for all of these. And I've got 5 different flavors of forecasts, if you will. So NRCS published forecasts, CBRFC official forecasts, which isn't exactly their direct model guidance, but it's usually pretty close to that. The ASO WRF Hydro, CBRFC experimental, which we just heard about from Cody, and finally just M4 raw model guidance. And, I'm going to say up front that I'm hesitant to draw big conclusions from such a small number of points. We have 42 total forecasts that we're comparing here across the group. And these are just simply looking at for all the forecasts, different basins, different publication dates, looking at the percent error as a percent of observed and rolling that up for the different methods. These are the results that we have from that. You can see the NRCS and CBRFC are sort of in that 9 to 10% average error as a percent of observed. WRF Hydro and CBRFC experimental are a little bit higher than that. M4 is closer down to that 9% average error. And then I threw in just a simple, just to sort of show you about this power of the ensemble. Throwing those 5 different forecasts into a single ensemble, it's like I was saying, like the average error is actually lower from that ensemble than any one of the individuals. So I'm still fascinated by how often that works that way. It's really neat. Obviously, average error is not the only thing we can look at. I've got some maximum errors and minimum errors. And then the other main point here is like, for any given forecast, though, different forecasts are the best at that moment. So, and it's very hard to know, again, like which one, well, what's it going to be? So I just wanted to highlight, this is not really about like, hey, any one is better than the other. This is more about there isn't a single one that's always better. And ensemble approach is really interesting idea and path forward that we're pursuing. I'm just listing where I got the actual, well, Carl pulled the actual forecast from these different sources. It has been great with Chasm. They've done a really good job to pull all the data together for these different forecasts. So we really appreciate the work they've done there. And that's basically it. I did want to just kind of throw up some big picture questions here at the end that we can chew on and continue to discuss. But I think there's this idea, it's already come up several times today, about how do service delivery organizations like the NRCS, what should our evaluation process be before we adopt a new approach, new standards, et cetera? I think it's really hard, especially in these where we've got these new modeling systems that don't really have traditional, hindcast capabilities, or the data sets are not available further back in time to do more rigorous evaluation of how they perform. And this is an open question. I don't have an answer for this, but it's one of the, I think, challenges when we talk about adopting into operations. That adoption is expensive and it can be difficult. So there is a balance between that, like what's that point before you take the leap? What evidence do you need? Where's the burden of proof, I guess, is sort of one of my questions there. And then also just as a community, what does a real community water supply forecasting model look like? I think I've sort of laid out one potential vision where we use multiple model structures and find ways to pull them together. But yeah, I think it's one thing I love about the group here is people are open to ideas about how to do these things. And so these are just some big questions that we debate a lot in our organization, and I just wanted to bring up to the group. Thank you.
Thank you, and great talk. I was wondering about those architecture that you showed, like 7 of those, like including ANN, SVM, like that is support vector machine and others. And then you talked about genetic algorithm there. So the idea is like you guys are optimizing among all of those and getting one specific model at the end, or optimizing all of those at the same time?
Optimizing each individually.
Gotcha.
And then the ensemble technique is just wrapping, you know, the results from each individual model together. But yeah, they're individual models, the 6 different techniques.
Okay, and then following up on that, like how many input variables you guys have considering for the time being?
Yeah, so currently we're still basically using the same input variables that we have historically. So we're primarily using our SNOTEL water equivalent and water year precipitation as inputs. That's what we're doing currently. But like I mentioned, now we have a platform to start exploring, you know, additional variables, and also experiment too with whether our approach right now is still to use a principal component analysis. So actually what we're modeling is very few, you know, input variables once those are combined.
So these are all daily data, am I correct?
Yeah.
Okay,
yeah.
Thank you.
Jacob. Hey guys, nice presentation. I think we have a lot more to talk about is what I'm hearing. One thing I just want to know is that on your exploration of new input variables, I would like to collaborate on that. Just kind of see what you're seeing. And this kind of ties to kind of how do we pick what to pick up, adoption of new technologies. It's been interesting a couple years just working in a group with a charge to modernize, you know, over here, service organization as well. And it's some of these models are really, really heavy, and building the capacity to operate them seems improbable, right, at times. And so he's like, if we go down that road, that's a long-term commitment to make something happen that we're not quite sure of the outcome. So that's happening, but I've been kind of in a position where I can kind of pick my own path a little bit because other things are being covered. And I find that some of the older, lighter weight tools are pretty handy dandy. It's just they need a bit more nimbleness added back into them. Like a lot of the frameworks and our software frameworks to operate our old systems are pretty rigid. So it's really hard for us to do kind of what you're talking about, which is test new inputs and adopt them and kind of fit equations that can account for those new data streams. So just a note, I've invested my development time into adding some flexibility back to those old tools, which is why I would like to, you know, I think about this time next year, I'll be in a good spot to be able to consider, you know, like some modeled soil moisture or something into one of our classical multiple linear regression approaches. So there's a lot I would like to talk about after, and just wanted to say good presentation, and we struggle with a lot of the same things.
Yeah, thank you.
Anybody else? Okay, I'll jump in because we took one on the chin right there, and that's all right. But I do want some things that we can come back to during the modeling discussion, which analyses like yours raise. And it's really more about the broader how we analyze models. That would include the benefit that entities like the California Department of Water Resources has done in developing these naturalized flow data sets. So a key aspect of, I think, a lot of these analyses is disentangling which of those forecast points is at a downstream location with managed flows and we've struggled, particularly in Colorado and Utah, to get naturalized flows in there. The RFCs make their own modifications. You guys regress it out more or less. And so, you know, I'm not giving ourselves an out. What I'm saying is that is an important part of the forecasting process, which we've benefited from immensely in California, and we're still kind of struggling to develop within Colorado and Utah in many cases that go into results like that. Yeah, there was one other, oh yeah, just looking at, you know, overall headwater performances, which again, is another thing that, you know, there's a lot of differences between these systems. So yeah, figuring out where things are working and where they're not, and also why they're working and not, is important context for all that. And I think we can continue to dig into all that.
Sure, yeah, and then, I did forget to mention, so the error calculations here were based on our data sets, which most of these basins actually, I mean, even the ones that are heavily regulated, we do quite a few adjustments. I know we talked about this yesterday. It's not a full natural flow, but it's, you know, 95% of the way. Hard to say exactly.
Yeah,
but it's a
but
good
we're all
point.
doing it differently is the problem.
Yeah,
you
and
know,
so
that's the challenge.
with the CVRFC, we're actually more or less congruent with. It used to be a lot more coordinated than it is today. But I mean, the reality is the adjustments don't tend to change over time that much in recent years. But I mean, they do. There are changes that can happen, and you need to account for them where you can. Our adjustments are based on, you know, largely what's available. So I mean, we know that we're going to miss some things there. So it's a good point. I actually, what it brings up to me though, is there's all this work that we do individually that takes a lot of time. And there is definitely work for us, you know, to centralize the way we store data, modeling data, observe data, which frees up all the time for the modelers to actually focus on the important part, as opposed to this, you know, there's this mundane data collection side, which, yeah, we all go through separately and end up in different places. So I think there's a lot of incentive for changing that.
Yeah, and we shouldn't be replicating, like doing the same thing that each other's doing. I do want to call out Emily Carbone. I didn't mean to neglect that there was great data coming from Colorado in terms of naturalized flows. So she's been a great provider of that. Jacob, did you want to say something else?
I mean, I think to me, it involves, you know, this process of first talking about it, seeing what our real resources are, seeing where the real problems are, not siloing ourselves, not really even competing against each other necessarily. I mean, that's to me what I would like to see it be, supporting each other, because we know this work is super important. And to some degree, I guess I feel that the idea that any one group or one person is going to lead the way on it is probably not realistic. So use the community.
I think power of community is trademarked by somebody else right now. Can't remember. Yeah, thanks again. So Peter, it's Finkenshire, right? Finkenshire.
Is this on? Yes.
Yes, it is. Got my accent wrong. From the California Nevada River Forecast Center, obviously well known to all the locals here.
All right. This is my first time at a ASO workshop. I know last year, I think Mike was able to tag team with Cody, and fortunately Cody covered a lot of the ground, background of what I'll be sharing. I also put on Alex Chen, Mike Kittle. They have been working on integrating in a similar way of direct assimilation of ASO data into our modeling. And so a lot of the graphs you'll see come from them. And hopefully, I know this is the last day, the last talk. So if people are zoning out, I can understand. That's quite okay. I was a little jealous hearing about Gus is getting more resources on a federal level. I've been with the River Forecast Center for 25 years, and we have had the same staffing for the whole time. And of course, over time, there's more and more demands and requirements placed on an agency like us. And so I thought I'd just throw this slide on here again to show our domain of responsibility, our 350 basins that we model every day. 365 days a year. And besides water supply forecasting, we're also very involved with flood forecasting, flash flood guidance, reservoir inflows, and of course, along with that comes all these new programs such as the forecast informed reservoir operations, working with the Corps and other agencies, kind of that group efforts that those require. FCO projects are also on the list. And then nationally, you may have heard that the River Forecast Center is actually getting reorganized. I don't know if you've heard that, but the Office of Water Prediction, which has been growing quite a bit in DC, they've been getting all the resources, and now they're actually going to pull all the NOAA water resources under OWP over the next couple of years. And so that'll be a change for us. Maybe we'll know more in a year or two what that's going to look like. But things like the next gen national water model, a couple of us are going back east to learn more about that. And that's one of those, again, high resolution models where ASO data could be really useful. And also flood inundation mapping is another program that's nationally on our plate. So I'm going to talk a lot about April 1st error and uncertainty. And this is a little bit of my kind of perspective, California perspective. Also Nevada. I'm sorry for those from the Nevada region. We're so close to Nevada. Mike Imgarden last year, I know, spent a lot more time on the Nevada Truckee River system. But anyway, in terms of an average year in the Central Sierra, I'd say 50 to 70% of the air really does come from the weather uncertainty, especially as you go further north into the American, Yuba, Feather Rivers. Those are where you really see a lot more of that weather uncertainty, and less so in the south. But kind of just my perspective on this past water year was that there's still a lot of uncertainty in that snow component. A lot of that is model, some of it's data. And then also for us, which I'm going to touch on a little bit, is how does that snow and the soil interact in producing that April 1st forecast? And so how do you do verification? I guess, one of the things that we try to do, and we haven't done this in a while, but we're doing it this summer, is, again, produce these long historical hindcasts. We have a hydrologic ensemble forecast system that runs on 44 years of data now. And so we can run each of those days for the past 20, 25 years. This was done on 85 through 2010. The new set of hindcast data has an updated period of record. But only after you kind of run through a long history can you really start to see the model errors. And you can see in each individual error, the green dots are what the actual observed inflows were and how those lined up with the 90, 10, and the red crosses there would be the max and mins. And then looking at a more of a, what do you call that? Just a histogram. You could see that for this one basin, this was the San Joaquin Basin, I believe, we had a definite error in the model in terms of we had tended to under forecast the drier years, the ones that kind of tended towards the last 20, the lower 20% of those years. We tended to have a lower bias there. And that's where operationally we come in, look at all the data we can to try to make our best adjustments to improve our model. So looking at any individual year, it's always hard to say what was the error, because people have kind of mentioned that. If you just look at the median forecast, that can give you one sense of what the error is. But it's also really, especially with the large amount of precipitation uncertainty, why not look at the percentile of precipitation and then use that as a way to verify your forecasts. And this is a picture from, let's see, San Joaquin River at Millerton. Again, the April 1st forecast circled in red. The dark black line is the median forecast. The purple is the 25-75 percentile range. Kind of the whitish area would be the 90-10. And so it looks like the April 1st forecast verified really close with what the actual observed was if you were looking at the median. The problem is it was a drier year. And so in actuality, I would say that, we were under simulating there, that we should have had more snow in the model coming into the April 1st point. So I'm going to show a few, again, graphs like Cody did. Again, but looking at, again, and pretty much in that San Joaquin region, primarily that's the precipitation that's going to have the greatest amount of impact on that verification. For 2023, again, we were all very fortunate to have a 90th percentile, very dry April through July period with that large snowpack. Looking at the 5-station index, May did have a little bit of rain and a little bit in June, but nothing in July. Temperatures also play a role, so that's something to consider as well, particularly in a very wet year like 2023. Cody already went through this. We pretty much followed the same method that he's been using of taking the 50-meter data, resampling it, and putting it into our standalone ensemble forecast system. And the other thing that might be a little different between us and CBRFC, we've been incorporating longer-term GEFS forecasts, ensemble forecasts going out as far as 35 days. So anytime you're looking at some of these graphs, any individual forecast on that day is actually including the weather forecast out to 35 days, although, again, it's calibrated so that those longer range forecasts are not going to have very much impact. So the goal, I guess, is we're trying to explore how can we find some consistent trends and I think in the ASO suite estimates, which we can utilize. So here's an example from the Tuolumne Hetch Hetchy Reservoir. Again, some of the early estimates would say that we were too low. Our snow is too higher and the ASO is lower. You can see those in the black dots in, what was that, January, February, March. But again, looking at where we came in on that dashed line, again, a 90% dry forecast or dry weather pattern would say that that April, what is that, 21st or so, 25th forecast, the ASO estimate was much better than our forecast, which was too low. And I'll explain the red dashed line in a little bit. Similar curves down at New Don Pedro. Again, there our forecasts were too high. Again, the ASO estimates came in much closer to the actual observed. And this is in 2023. And then X-checker on the Merced, and we're not sure, I have to go back and kind of verify exactly what happened here, but the ASO estimates were much different. Again, this could be, again, the problem of trying to directly assimilate a snowpack into our model, which is a combined soil and snow model. We're calibrating soil parameters, which might be biased or causing a bias in our snowpack. So we're creating a bigger snowpack in order to satisfy the soil parameters that we calibrated to. And that's what I think is kind of going on there. I'm not totally sure. And then here at Pine Flat on the Kings River, a similar case where we made very few model adjustments on that. And so again, we were slightly, if anything, we were slightly too high or too low on April 1st. Again, taking that 90% where the line is drawn, taking that 90 percentile forecast, that's really what you want to see closer to that dashed line. So that was water year 2023. Now in 2024, similar, we were still on the drier side, but we did have more rain, particularly in April in the San Joaquin region. And looking at the historical record for the precip index, comes in at about the 63rd percentile for April through July, and then May through July was the 75th percentile. And again, with the average snowpack, you didn't have to worry too much about temperature. So again, looking at Hetch Hetchy, they came in right about dead on. If we had used the ASO SWE, just again, nudge the SWE down on April 1st, would have come in pretty much right on that 75th, 63rd percentile. So that was encouraging to see. The May 1st forecast ended up would have been too high. But again, looking at the 75th percentile, but we were too high to begin with in general there. You might start to see a pattern between where I'm circling the really good forecasts and the ones that we were having trouble. How do we use those? So this red dashed line, this is New Don Pedro again. Again, the April 1st forecast there, we were again too high, but it seemed like ASO was too low, but split the difference, it would have been about right. But again, a much better forecast about May 1st would have been, again, if we had used that ASO data on May 1st, it would have had a better forecast. X-Checker came in much better on this past year. Again, the SWE data comes in a bit low. Again, the pattern is, I think the early season ASO analyses tend to always under or be below the SWE that we have. But then past that red dashed line, they tend to get closer. And so I started thinking, why is that? And in looking at our model, there's one of our parameters just absorbs a lot of the initial snow melt. And so if we have a large soil parameter that's absorbing that snow melt, we're trying to create a bigger snowpack to absorb that water so that the final flow ends up being what we want it to be. And so it's giving us a little bit of a clue of like, hey, maybe these later season ASO flights will be a lot more useful for us going forward. And the best example of that was San Joaquin at Friant. Again, we were pretty close, and that was one of our better forecasts this year. And so again, the early season ASO estimates would have thrown our model off, but the later season ones came in right where we were expected to be, which again is that 75th percentile or so forecast. So there's some progress there, just taking the time to kind of look at this data. I think we're finally starting to see ways in which we can use the ASO in our operational forecasting. And so considerations here. Again, the May ASO estimates seem more aligned with our SWE. And so being more aware of model changes, we're trying to work also to help people to know when we're making changes to our SWE so people can notice that. And hydrologic model error and error in future weather assumptions, RFC, we've started to notice also that our model, you can see some of those graphs had some wiggles towards June and July as we struggle with some of the precip that comes later in the season. And finally, so again, while we haven't seen the consistency, I think we're starting to see a pattern of again, our model biases, and came back to the question that I think was addressed earlier, how can we start using ASO SWE in our calibration so that we don't have to deal with this, the soil problem that we have that affects us. Anyway, I think I'll stop there and take questions.
Great, thanks a lot, Peter.
It's a question for Kat, actually, but comes back to the Merced. We are extending the snow-free area for the Merced this year, and I'm gonna guess that the huge excursion that you saw there was because we weren't capturing all the 23 snowpack.
Yeah, the low elevation.
That's right.
That's right.
Is that right, Kat? Yeah. Okay.
Okay, good.
So
yeah,
many thanks to Ramesh and Dave Rosardo for providing the funding to shore that up.
Cool.
No.
All right, other questions for Peter on the California side? Eli and then Ramesh.
Oh, Ramesh.
You already got the mic.
Okay. My question was just, so it looked like most of those places where the ASO informed forecast was more erroneous were tending to be in the late season. Is that right? Because I was wondering if, as a result of the direct insertion, the snowpack is basically, or volume is basically wrong for two reasons. It's either the precipitation or it's the timing of the melt and accumulation. So in my experience in California, it has often been because of the timing. So either you're melting the snow too early or too late. And then with the direct insertion, you're effectively either vacuuming out mass if the model didn't melt it too soon, or you're adding in extra mass. And so I'm wondering if that tendency to accumulate large percent errors in the late season is a result of double counting or undercounting the mass through the direct insertion. Or basically melting the same snow twice or not melting it at all.
Yeah, that's the danger. And that's why we've been wanting to study this more and more, so we don't do, damage to the model by inserting twice. And we're looking at all sorts of different ways to adjust our snow. But using some analysis like this helps us to see, well, yeah, maybe there is when we've kind of filled up a lot of that soil moisture, the ASO numbers could really teach us or lean us one way or another.
Right. And I guess just kind of follow on to that, I wonder, have you thought about accounting for that mass balance somewhere else in the model? So if you pull out a bunch of snow, adding to the antecedent stream flow or vice versa? Have you checked whether that mass, if you subtract the amount you're pulling out of the snowpack from the, say, March stream flow volume,
right,
whether that's going to shift you back kind of on track beyond just the soil storage in the model?
I'd have to, we'd have to totally change model parameters, I think, at that point. Otherwise, again, it's a continuous model that if we don't make a lot of changes midstream unless it's really desperate.
Thank you, Pete. Great presentation. Yeah, just curious about any other plan to compare similar results for other watersheds as well?
Yes, we again lack of resources. I wanted to do some stuff in the Yuba and American this year, but hopefully we'll get some more help in the future.
Okay, thank you.
Let's go with one last one before we take a little break. Kazungu, do you want to go?
Yeah, so same here too. That was a great presentation. And just for your information, I was bred and developed by the National Weather Services too. So my knowledge, knowing that I've been there for a long time, I feel that our models have some structural defect, the ones you're using. So as long as you don't address that, all you'll be doing is just bringing in a band-aid solution just to satisfy your current need. So my request to you guys is you may want either to demolish the whole thing, build it, or something like that. But anything we are doing right now is just band-aid solutions. That's what we are doing.
Yeah, and I think
Thank you.
I'm hopeful that there will be this transition towards higher resolution distributed modeling as we move towards next gen. And they're wanting to hopefully include a lot of the operational insights into the development of those. And so there'll probably be more to report on that.
Yeah, I think that would be good because some of us who depend on your information to drive the economy, honestly, we get frustrated when we know that all you're doing is just going around the problem.
Yep.
Okay.
Just one more thing though. The one advantage of using simple models, and I think Gus referred to this, every model has its strengths and weaknesses. One of the benefits is that we can run these multi-year, 365 days ensembles every day, get them out there for not only water supply forecasting, but also short-term flood forecasting. It's the more complicated your model gets, sometimes your output resources gets constrained as well. So there's give and take on each side.
Great. Thanks a lot, Peter. That was great. we are going to take a 10-minute break, and then there will be sort of an open modeling discussion after that. Everybody's welcome to attend, no credentials required. All opinions welcome. But if you don't want to stay, you don't have to stay either. So Molly will still give you a ticket later so you can go up and have the dinner and everything. But we would love to have a great discussion on some modeling stuff. I would guess it'll last 30 minutes to an hour at the most, just to circle back on a lot of what was presented and talk about some future directions and collaborations.
It'll have to be cut off.
It'll have to be cut off.
The discussion it could go on for a lifetime.
Oh, no, it won't. Heck no. All right, minutes, we'll be back on. Hello. We're going to go ahead and get started with the modeling discussion. Ready? All right, we're going to start the model discussion. So find your seats. Don't make me sing again, because I will. I do not need encouragement. All right. Are we ready to get going? Folks in the back, are you joining or not? When you're in, you're in. When you're out, you're out. But when you're only halfway in, you're either in or out. There you go. See? All right. So this is intended to be loose. It is intended to be discussionary, blue sky, if you want to go there. These are just potential topics that come up when we start talking about modeling. And I liked Gus's metaphor of sort of the modeling community writ large. We're not looking at this just from the ASO perspective. We're looking at it as how we can improve our models to improve forecasts. And so as I was listening to the various speakers, and then most of this came out of this afternoon, but there was a few earlier ones that some themes that kept coming up. These were some things that certainly did keep coming up. Now I'm happy to throw other things in here. I'm going to start with the topic of flight timing, because we appear to have gone through a whole evolutionary cycle of this, as was mentioned earlier, where there were some flights that we always tried to get peak SWE, because that's one of the traditional metrics. And then it was decided we should probably go earlier in the season to help lock the models in earlier in the year and try and decrease some of the uncertainties in the longer lead forecasts. But then, as we've seen for the last couple years, particularly in 2023, where we had the massive snowpack out here, a pretty large snowpack in Colorado, getting those later season flights helped us understand some of the shortcomings and areas of improvement needed for the models in terms of the ablation process. I think the earlier talks this week by most of the operators talked about how the flight timing may sync up with key decision points. And so from a modeling perspective, there's been this larger evolution of things. And so I wanted to throw that up to see if there was more discussion we wanted to have with that. One of the things for us that has come out of the Colorado program, where we have far fewer flights to schedule and bracket around through the season, has been this need to try to get flights, not necessarily very, very early. That would be great if we had a larger number of flights, like into February, but at least before we start ablating snowpack. And I think, as pointed out by several of the modeling talks this morning, it is that ablation process that we can see a lot of different behaviors in the model. And so locking in the model snowpack state before we get large sources or large scale ablation going on does help us isolate that source of error. Basically, we're calling it most all, precipitation accumulation errors and maybe some redistribution and some sublimation, but not large scale ablation. And so I think that was, we saw that pretty well in Colorado this year. The basins that we were able to do that had benefit, and compared to some of the basins where we couldn't do that. Other thoughts from a modeler's perspective on flight timing? I'll pick on Mark since we've had lots of discussions about this. What else do we need to be capturing?
We had the Uintas, I think, is the best minimum scenario, a best realistic minimum. There were 3 flights in the Uintas. The first, oh man, I'm not gonna remember the dates. Does anybody? It was early March, right near peak, and then maybe what, early May? But they were, anybody in Utah? But yeah, that for future use, and I know less about how it's that, you know, the ASO data is being run in a hydrologic model, but in terms of leveraging the flights for skill for our purposes, it's not that useful if we miss a big accumulation event and there's melt afterwards, because you don't know if it's precip, you don't know if it's ablation, you don't. So, you know, 3 flights, 1 early, 1 near peak SWE, and 1 during the meltout, in my opinion, is the minimum that we would need to have some confidence in at least our ISNOBAL.
Yeah, I would agree. I think that makes sense. What do we do when we have 1 flight like we do in the Front Range in Colorado?
I'll talk about that too. I think from my perspective, I think aiming, because there's I'm tangential to some of those conversations, but I get their interest in peak SWE. I think it makes sense to shade a little bit early. For multiple reasons. One, weather, and if you get bumped back a couple weeks, you still hit peak SWE. The other is that what I just said about the Uintas, you know, if you happen to miss late, we don't know if our error in the model, we still don't know what peak SWE actually was. If you hit the flight when you're even somewhat down to the ablation, who knows?
Right. Peter, do you guys have a thought on this as well? In terms of where you would, in your system, where you might see more benefit or less benefit with limited flights? I guess, yeah, you're in California. You have riches of flights.
Yeah. Yeah, we have so many to choose from. It hasn't been an issue. Certainly peak SWE, and I do see more differences in models. The uncertainty of snow modeling happens more on the ablation side. So I would definitely lean towards that end of the snow year. The advantage on the California side is precip being orographic tends to be a little bit more predictable. So the early seasons aren't as important, I guess, in California. That'd be my take.
Tom, go ahead.
Thanks, Mark. I was looking for Olivia and Wes, and I realized neither one of them's here. So I'll just pick on them. So it was interesting to me that Olivia was pointing out that they needed more late season acquisitions, and yet the main instigator of earlier flights in the ASO program was one Wes Moynier. And so, I mean, I think that really speaks to what the nominal program looks like, where we have sufficient acquisitions in the accumulation season, and we have the right number of them during the melt season. But how best to afford the limited ones, I think even within a single organization, there's going to be tension over that, because Wes has customers, and Olivia, even though they're right there together, they have slightly different customers within their orgs, and so I think it really becomes a basin by basin and perhaps organization and even person by person question. So that's why we need the full program, right?
Adrian.
Yeah, so as a scientist, I don't have to be realistic about how much data collect, but you know, putting that sort of caveat there, if you think about them as pairs, where you're differencing you're looking at the change in snowpack between two snow-on collections. I think that helps to make Mark's point, which I've also seen with more empirical analysis, that if you have accumulation and ablation between flights, you're confusing yourself. You can't extract back out without some kind of time series. So from a science point of view, back to sort of like my talk, it's like if you compare two flights that you know only accumulation happened between them or only ablation happened between them, because you had the same problem in the ablation season, right? You still get accumulation. That is really valuable, I think, from training models. It may not be as good for water supply forecasting, but there's a lot of value for training models and doing empirical things.
Yep, completely agree. Ramesh, did you want to say something? Let's see, we need a mic runner. Thanks, Mark.
Yeah, I'll throw it.
Mark the mic runner.
Thank you, Matt. Yeah, as Tom pointed out, I think we got to look at the watershed elevation and then the type of watershed, especially like when we look at between feather versus kings. And also like, you know, those watershed, like we have seen clearly distinct different when that melting starts. So that also tells us, okay, when and how we can have that flight timing. So I guess that is one component. Then the other is, of course, like, you know, ice snowball model spinning setup. So initially, so as we discussed, like after our Thanksgiving, going, you know, back and forth without discussion with all the cooperators. So we're trying our best, as you all know. We're hoping for more flights if we get some more opportunities for additional funding. Thank you.
Great, thanks. Gus.
Yeah, I was just gonna say, like, it's a hydroclimate thing too. So some places we're always gonna have melt between flights no matter what time of year it is. So it's also like an opportunity, I think, like Colorado being a good example where that March flight, we get a lot more information then about, you know, what the precip patterns are too, which you start to lose as soon as you get that intermittent melt. I know that's not new information, but just wanted to reinforce. I think from my perspective, that's a really valuable picture to get before where possible, before melt has really started. Oh yeah, I think that's a little different. I mean, I'm thinking about longer times between flights, but yeah, if there's certainly like would be amazing data to collect if you're doing it like before the storm, after the storm, that would be amazing.
From any of the operators, like Steven, you want to throw in a comment on any of this?
The weird part is it depends on what the year is and what the year was. If it was a wet year before, we are starting the year with a maximum carryover, and therefore our needs are different. If for us, when we have max carryover, we only need it to be a dry year and we'll survive. So if you know for sure that you are not dry, even if you're below normal, and that you will come out of the year basically right where you start, your priority are completely different than if you were very dry or if you're facing a wet year. So that's why I think ASO and NWS already have our list of preferred dates, and some of those, you know, March and April is because of the Bulletin 120 use. So I'm pretty sure the early flight was to nail down the Bulletin 120 the closest you get to it. And then after that, like other basins also say, after the peak, during the melt off, before our Army Corps manual hits on, you know, when can we cap out on the storage, That's when water managers have the most flexibility on crafting your rise before your reservoir starts to drop. And any benefits there usually does not benefit water supply because, again, we already end the year with the high carryover. All the extra usually goes to either our benefit or environmental benefit, like Olivia's presentation last year. So all that optimization benefits everything else, which is good. So depends on the year type and the year before, which is odd.
Good consideration. Emily, do you want to throw in on any of this?
I don't know if I have that much more besides what I had said during my presentation, but we have 3 flights a year as part of our 3-year project with reclamation. So the earlier flights in March, which we hadn't been able to get before this project, have definitely been valuable this year. And like was said, that can inform the models and give you a more accurate picture if you miss peak SWE or before you can get your April flight. And then we try to get around the peak SWE and then also later on in the season when we have less information about the snow tells. But yeah, there's decision points early and late in the season. So yeah, as often as we can afford to have the flights is nice. But yeah, having one early and one peak and one late is really what we'd like to do.
Great, thanks. Unless anybody else has anything on that, we could move on. We talked quite a bit over the last couple days about some opportunities for model improvement. I think Adrian humbled us sufficiently this morning on the state of things, but there's obviously a lot of individual threads that are addressing a lot of those uncertainties that are going on now. Some of them are physics related. Eli had a good talk on updating some of the physics. It's nice to see the wind redistribution getting into some of these. I guess what these kinds of improvements do bring up are what other kinds of key data are needed for us to do that. So things like wind measurements, humidity measurements were needed. We know the landscape information is constantly evolving and constantly needs to be updated. And I've been dashing out some emails to various folks saying, how bad was the fire you got in your basin this summer? And do we need to really take it into account? Did it happen in a major snow runoff producing zone or not? Or is it not going to be that big a deal? And so I think things like that will happen. Any other thoughts on key data? I'm not talking like, yes, we need a better geologic map and soils map. We all know that that's real. We all need that stuff. It's not going to emerge, but other key data sets that folks feel like might be out there, but we're not using sufficiently at this point in time. Excellent. I prompted him sufficiently because I wanted him to help answer that.
Yeah, what I'm seeing across the board on different models is different incorporations of QPF. So, how much lead of short-term weather do you consider medium-term weather? If so, how so? We're recent adopters of a 6-day QPF put out by these guys, and we've tinkered with another one as well. But we've gone through a lot of pain points as far as adoption of that, and we can talk about all of that. So it's not like super smooth and everything, but we did do a hindcast scale analysis, and for us, through our system, it showed a systematic improvement on all basins adopting that product. I'm seeing a handful of folks with models that have 0 QPF incorporated. So I'm like, well, low-hanging fruit right there. I'm also acknowledging that CNRC considers 35 days of QPF effectively, but there is a lot of desensitivity to longer leads in that process. So there's a lot out here for us to figure out, what do we consider, but also how do we consider it? We've been kind of playing with an analysis to kind of by lead day, by location, by event type. How do we sort of transition away from that QPF value and towards maybe like a climatology for that station for that time? So there's lots of things to do here on incorporating QPF. I just want to acknowledge that there's that for us across the board, I think.
Peter, did I
Yeah,
see you grab a mic?
Just clarifying. Yeah, the 35 days is primarily for temperature. And all of our QPF and precip and temperature forecast is calibrated. And so it goes through a historical calibration. How was the performance compared to observations? And so your correlation, your confidence is much higher in the early few days, and it goes down as you get further out. And so that helps to prevent a lot of ups and downs that you get from, in an individual weather model forecast.
I'll throw something out that's a little bit different, and that's NRCS's super sites. It's a coincidence in a sense because we haven't been involved in that anyway, but we're going to be able to immediately leverage all of that data, the temperature strings that Gus talked about already, but also RH, wherever else gets put in there. And, there's not an immediate path for us to be able to assimilate that data necessarily, but it will be incredibly powerful for understanding the model bias in the first, few years of usage or whatever. I also think there's an opportunity here, a big one, for us to continue to work together. We're lucky to have the SuperSite initiative. I think I know a little bit enough about it to know that they have these sorts of remote sensing and modeling applications in mind, but we need to keep being in the same room because we don't want to duplicate effort. We're here, we're all looking at the same thing. We should be working together like we are.
Yeah, totally agree. I think last year was the first year I felt like there was actual, besides pit data, when somebody goes out and digs a snow pit, some other measurements that we could get some snow temperature profiles from. And it's one of the biggest challenges we have coming right into the initiation of ablation and the timing and how quick it's going to move up slope and everything. So I agree. I'm excited for more of that to come online. Tom.
I wanted to follow on what Mark was saying, and I was going to wait closer to the end, but I think it's worth throwing out there right now as a bit of an umbrella for all of this, and that is that I feel like together, and so not just the California contingent, but everyone with respect to the modeling and model comparisons, I feel like we need to work together on having a framework for the model comparisons and really a stratification of those. So I feel like for the RFCs, you guys are in a bit of an awkward spot with, okay, here are the ASO data. We are not in a position right now where we can recalibrate to those. And so you're forced into a direct insertion it's uncomfortable, and it's, okay, how do we squeeze this? So how do we work together to start stratifying the discussion on each of these? And so likewise with Wharf Hydro in the Uintas in year one, do you want to throw that up against a model that's calibrated on 40 years? Probably not, but who knows? Maybe you get lucky in that first year. But really breaking that apart to make sure that we're talking apples to apples, and that we can make the kind of progress that is there before us to make. And I think that hits across much of what's here in the bullet list. So one path for doing that is to go to NASA headquarters and get funding for it. However, not everybody in here can receive NASA funding, and it wouldn't really necessarily do any good in that respect. But perhaps we can act as a coordinator of those discussions and at least try to lead that in facilitation going forward, and make sure that we have a regular schedule if it's quarterly, but work towards documents that describe this and iterate on those with the community. So
I'll make Gus and I were talking about something similar. I just want to go back to my point about benchmarking. If we want to benchmark the water supply forecasts, you can compare them directly together. I think that's a fairly tractable one. If you want to benchmark the models that are making those water supply forecasts, then they have to be forced in a similar way. They have to be treated similarly, or you're not going to know why you're getting the wrong reason. So there's two pieces. I think the benchmarking of the models is much harder than the water supply forecast.
Absolutely.
Other unexploited data sets. Sorry if I just jumped over some.
Eli.
No.
Oh, just on the physics, I mean, there's adding new processes, of course, which is always fun. I just got to add wind to a model this week, which was a great exercise in debugging C. But I've found, I guess, with my experience with distributed models, is just trying to understand what the process we're describing is and whether it's actually in the model in a meaningful physical way. And I think for that, it would be helpful to have a lot more like diverse visualizations. So, you know, we have SWE maps, we have hydrographs, and you know, then occasionally there's other plots related to coal content or typically snow metrics. But, you know, something like the expansion and contraction of a stream network through time or stream network disconnection, I mean, that's an interesting thing that these models may or may not be doing, which we may not be visualizing. And so I think finding creative visualizations of the physics that we think we're implementing and seeing whether it matches what we think it's doing is pretty fun, but it's also a real challenge with these models that are so complicated that it's hard to think about kind of how you would visualize some of the physics that we think we've implemented. So I guess it's kind of open-ended, other than I've had a lot of improvements that I had to make to the model when I visualized something I thought it was doing and turned out it was doing something that was maybe not so physical.
Yes, definitely can sympathize with that. Solution.
I think you discussed about this morning about human-induced like effects in the watershed. Like WRF Hydro right now doesn't do the lakes, reservoirs, and also like agricultural water use that's not there. Is there any like, are we looking for improvements in terms of using like OpenET database or like SWOT, the NASA 6-hourly soil moisture database to improve the models? Like, is that a possibility for this year, next year? I mean, we're looking into that.
No, I think there is good opportunity to use a number of the things you said. The questions I think do come from a modeler perspective is exactly how do you want to use them? So as Adrian was talking about, there's a lot that can be brought to bear just on diagnosing your model, you know, using data to diagnose it. A lot of people come to me and say, I've got a bunch of soil moisture stations. Can you assimilate those into your model? And I was like, God, no, I don't want to do that because there's certain issues with it. And it's a challenging, very challenging problem. But the use of that soil moisture data to diagnose your model in terms of its behavior is very important, and it's very useful, right? So getting that basic understanding, I think, is with a lot of new key data sets is good. OpenET is an interesting one. We took a deep look at that with National Water Model Development and other folks. You know, it is a retrieval product, like a lot of products are, especially from the satellites, right? Which means they're not a pure measurement. They have a model underneath them as well, which has its own, you know, sensitivities and uncertainties. So I would agree, it's good to use those, particularly in those managed environments if your models aren't using that, and you might be able to use some adjustments or use it for tuning. But one has to use some of these other products very carefully as well as you get into them.
Yeah, I mean, I was thinking more towards the end of the season where we don't have too many like flights, and the ablation actually like some of these watersheds, so very different ones in the model, and you have no idea how it's happening. And during these times, the ET models might work better than where there is snow. So, I mean, looking into that, I was thinking of it using more towards later in the season than earlier in.
Yeah. Yeah, I think that makes good sense. Let's see. I think Jacob wanted to go next again.
Just riffing on solution a little bit there. Soil moisture. People solve for it a couple different ways. But as anybody picking an external soil moisture data set and incorporating that into an operational water supply forecasting? If so, what are you picking and why?
As an assimilate or just as a reference for
As an
model
assimilate,
behavior?
so you would use it as a,
I would say no, personally.
Anybody?
I think it's more useful for an ET forecast if you're forecasting ET, or you're using it to help constrain your lower boundary condition in a coupled atmospheric model simulation. But to generate runoff forecast, it's, there's not a ton of utility in it.
Okay, I'm trying to get at who's the best soil moisture product supplier out there for inspection for consideration of use.
Who's the best guy?
Yeah, anybody got a good sense of, I mean, he mentioned a product, but I don't know all the diversity products or kind of what one to consider and why would you pick that one? Anybody kind of got getting a sense of how well the watershed is primed in the snow zone effectively. So how efficient is a snowmelt is going to be in producing streamflow runoff is kind of what I'm trying to get at. So that would be my application.
Yeah, I did too. I've got some ideas, but
A working group on soil moisture I'm involved with. I don't know if anybody else in the room is, but my short answer is none of them are good at all. I mean, the land surface models are terrible. They don't do the physics right at all. They're subject to all the errors of ET and precip. And anything that uses, the SMAP sensor never worked right. So all the active radar stuff, I think there's some things that are coming online that maybe other folks know about NISAR. There's a handful of things that may be coming online, but I published a paper with Gus where we use the NRCS soil moisture data, and it's got issues we could discuss, but I think the raw data still is the best.
yeah, I'm gonna lean in favor of in situ soil moisture. That's what I think you're saying, basically, as references for hydrologic behavior in certain locations, topographic context, things like that. Obviously, no remote sensing product's going to give you a spatially distributed estimate of snowpack or of soil moisture under snowpack, right? And that's kind of one of the biggest challenges we have, right? So there, it won't work. But anyway, but yeah, this is you make lemonade out of lemons, right? Best you can. But I would be advocates for even more station measurements because you get estimates of variability, you get spreads, you get a lot of different time scales of wet up and dry down that I think help you understand your models better. So anybody else on the topic of key data? Tom, anything exciting new coming out of aircraft in the next couple of years folks should be aware of?
One thing that I'd like for us to explore is the soil profiling with some of the longer wavelength radar and seeing how that can be useful or if that's just cluttering it up and you just gotta recalibrate in a different way. So that's one, and then NISAR. There in some of the shallower snow areas, there's the possibility that can get snow water equivalent, but when there's wetting up, that's going to throw off the phase coherence, and but I think wet snow determination that's a good product to have. There are other radars that are up that can give that, and I think that's a product that we have not been using that we definitely should look at, and And then the optical sensors are definitely moving to the higher spectral resolution combined with spatial resolution. So what Michelle was showing earlier today with respect to MODIS, that's going to continue to gravitate towards finer and finer resolution and be able to really address those finer models that are addressing the landscape with better granularity. You think of anything else? Yeah? Please bring it.
Yeah, I mean, just the passive spectroscopy. You know, I was talking whatever day that was, about this ND mask where we're trying to hide all the spectral variability of snow so that we can get snow versus no snow. I mean, I'm finding 5, 6, 7 dimensions of signal in the snow we're measuring. Now, some of them are ephemeral, like how many hours has the sun been shining on it that day? But there's several dimensions in our spectral data that, you know, grain size and all the things you know about. And I don't know. I mean, how does that feed back into what this question? Well, I drag the dead horse out of the barn and you kick it some more, you know?
That you're right. I didn't exactly mention it, but I was heading towards that. It was just with the new optical data and the spectroscopy and the more accurate albedos, and not just for snow, but for vegetation and for characterizing soils. And there's an indication of soil moisture and the water status of the veg, et cetera. So, and those are not available from the multispectral data. But from the imaging spectrometers, they are. And as we get deeper and deeper into that, then we're getting to an amazing place of quantifying the state of the watershed and everything in it.
Yep.
We just need a spectrometer underground.
All right, before we wrap up, and we do have to wrap up soon because these guys need to check out for the day, and they've been doing an awesome job. I really want to say thank you to the AV team. Thanks.
You show that to your boss, Dallas.
I think
that was all for you.
You guys are playing the party tonight too, right? The DJ at the party? Oh, no? Oh. All right, well. Last thing I wanted to say while we got people here was, especially from DWR and many of the user stakeholders, you've got a bunch of modelers here. You got your federal modelers, you got your contracted modelers, you got academic modelers.
State modelers.
What's that?
You got your state modelers.
State modelers, that's right. What new products, what other products could be more useful for folks? I think we heard a bit this week at getting higher time frequency of forecasts out is good, at least down to weekly. It sounds like, you know, with the cadence of people looking at especially seasonal operation of infrastructure, I'm not talking day-to-day power demand and stuff like that yet, but we can talk about that. You know, what other products could be harvested out of the models to do that, recognizing the different models are doing different things too, right? Some of the models can give you gobs of different kinds of data. We've talked about things like ET forecasts in the past, and I think, you know, on our side, we're going to continue to pursue that in addition to hydro forecasts. But I'm just curious for what other products, whether they appear in the nice dashboards that are evolving or in other ways in reports or anything like that. Is there folks been thinking about anything, saying they wish they had something that they're not getting at this point? Come on, Stephen.
Yeah, no,
Throw me a bone.
I can think of something. I think with every report release for ASO Wharf Hydro, it should come with a song.
A song?
Yeah.
A backing track, like a whole, like.
No, from you.
Yeah, that's what I'll do.
Okay, yeah.
Cool. I'm gonna hire these guys to be like running it though. Producers. Yeah. Stephen, any products you want to see? Yes, thank you.
I said Stephen has to go after me because I feel like this could be taken as positive, but we should end on a high note. A forecast product that I would really like to see more standardized as a need is verification of what you've forecasted, actually. As an operator, I want to trust your product, but at the same time, I kind of work on trust for my operations unit, for communities about the decisions I make. And before I can trust a forecast product, I need to see it verified, and I need to see it verified on the range of scales. And I know this is the first time we're doing Wolf Hydro and Ice Snowball and all this other stuff. And so I'm not harping on you guys, but given that now we have a year worth of data, I want to see how did it do in this average-ish year. And then I want to see over and over again, how was this tested over the actual hydrology? I know this is a huge ask, but I've heard down the line that maybe you're thinking about doing some verification products, and I would really like to see that more frequently on all model products.
Okay, yeah, no, I think that's a great point. I can speak a little bit to what we've been doing at ASO. I think workshops like this are one of the venues that we try to push some of that out. We've been trying to do individual end of season meetings with every specific basin, and we haven't gotten around to every basin yet about what happened the prior year, what products worked, what didn't, how did the forecasts actually validate. And so what I was able to present earlier this week was what we've been able to work up to date. I think Gus's analysis was good in terms of pulling together a number of different forecasts and pulling that together. But I'm going to give Jacob then a chance to comment on DWR's wishes for hindcasts, which I think helps address the question that you have. And we can have some discussion then on the challenges of doing hindcasting. But yes, we've talked about this, and I'll let Jacob sort of kick it off.
Yeah, we've had the same sentiment. We've been, we're modelers, but we're also sort of ingesters of models of the same type. So and there's a lot of new technology that we're playing with here, and it's kind of like, how do we make sense of it? And yeah, that's the golden, give me a 30-year hindcast, please, and give me some stats that summarize that. Love it. It's not practical in all considerations. So we're going through an internal process, kind of figuring out what our preference are as far as looking at air, so developing the metrics themselves. But then once we kind of get a consensus on that, we've kind of have a sort of a tiered ask to our various suppliers for sort of run back times for consideration. 30 years being the ideal, 10 years kind of being like, if for some reason compute or something like that, but all the data streams are coming in and you got 10 years, well, give me 10 years, and then for some of our areas where we got short period of records, like give me at least 3 years. We're fortunate enough that the last 3 years have been a dry, a wet, and an average, so we kind of get a nice, nice look that way. But generally, that we're, this motivation to have a multi-method air, evaluation is, what we were looking for to make sense of everybody's stuff when we had to make the decisions themselves. They're like, you give me a number, but I don't really know. I know the ins and outs of this other model, so I'll trust it just because I know it. But that's not a good feeling, right? So Lauren just pinged me just in the break right before this breakout, and he's like, "What if we just did like a multi-method the end of this last year dashboard? Why we just did that?" I was like, we don't need to have all the hindcasts and everything. We just say, how did everybody's turned in their stuff and how'd that look this last year? That's something we can execute right now. So we should just do it. So we'll do it. And she said, we'll do it stat. I was like, so I don't know what that means exactly, but fast. But no, it's been it's been like 45 minutes, man. But generally, I think that's what's actionable right now. This is looking at what happened this last year, and this sort of conversation and requesting enough data from all of our suppliers and contractors and ourselves to be able to compute to do a hindcast in a semi-fair way. It's fraught. Hindcasters, we talked about forcings. Adrian is talking about if we don't force all of our stuff the same way, it's not really a nice apples to apples. And the world's dirty out there, so we got to kind of make do with what we got. So I think one of the things we're talking about was requesting at least the output of everybody's model over time so that we can at least summarize the stats ourselves. And that's kind of one way that gives us a little bit more confidence in, how the numbers are actually shaping up. So we're trying to make sense of it, and yeah, we're working on it.
So I'm going to add one thing to that before Lauren jumps in, because it touches on one of the things that Adrian was talking about, in which we found to be a challenge, because the question obviously comes up: how did your model do versus somebody else's model? Oftentimes it's, the ASO Worf Hydro versus the RFC or the NRCS or some of the other major ones. And it does get to the need for a standardized approach, but I want to just like push back slightly on one thing Jacob said. It's like, we're going to do it and then we'll go off and compare the models. But there's some context there that would be nice to have that the modelers actually engaged in. That is, deciding and blessing what is the verification data set that's being used and making sure it's consistent with what that particular model is actually trying to predict. We all say AJ flow or something like that, but as Gus and I were kind of talking about at the end of his talks, there can be some differences, some pretty big daylight between what we were grabbing and using in our forecast and blending in and ultimately calling truth by the end of the season versus what they used for their end of the season metric. Those numbers can diverge sometimes, and it's just stuff we have to be aware of, and we all say, okay, this is really what we're shooting for, because it puts the analyses on an equal footing in that way, and you actually learn more that way as opposed to conflating some of the results. So don't forget the modelers, and I know you don't, because we talk all the time. So, but yeah, I think it's a good thing. And from the state and the agency's perspective, coming out with blessed data sets that we all like to use, like the FNF data, is crucial. I mean, that makes our world so much easier, that we all agree on what truth is. Even if that truth is flawed, it doesn't matter. We at least agree on what it is we're shooting at. So yeah, but Lauren, you may want to add.
Just kind of in response to Caitlin, like as Jacob has said, we're really grappling with what kind of error metrics to look at and which ones are most valuable. And I think you're a little more focused on the near term and we're a little more seasonal, but where you do have metrics that apply to like the Bulletin 120 kinds of forecasts, I think we're super interested, because I mean, you're kind of our customer, and what matters to you matters to us. So like, if you have a metric that is a good way to describe what you care about, like that's invaluable to us.
Dave, or somebody.
Gus had a
Go ahead,
comment.
Gus.
We will need to wrap up, so maybe a couple more.
Yeah.
Just going to support the, verification is, in my opinion, the foundation of really any forecasting thing. So it's got to happen, really. Recognizing the hindcast issue with some of the new modeling systems and DAs and all that, yeah, we can't exclude those models. We know there's conceptual value and we want to harness it. So, but it is a new paradigm, because we're used to this, like, well, of course we can produce hindcasts and evaluate those. And now it's a bit of a different world. And then with regard to the observed data sets for comparison, I don't think that's just a verification issue though, right? That's like, our operators need to know what we're actually forecasting. and if there's nothing to verify it against, that's obviously problematic. I'm all for, let's not do redundant, adjustments that are different. If we can figure out how to share that responsibility and have a, central repository for that, and maybe there's an opportunity with NOAA to do that based on what the RFCs are talking about. I don't know, but I've always dreamt about that, but knowing how hard, that kind of cooperation can be to actually make happen has been prohibitive.
And following on the last few comments and what we were talking about earlier, I think we have to be really careful about the model comparisons as well. And I'll just tell you, Dave Dave is happy to wade into it with the WRF Hydro results, even year one, throwing those out there, and that in that case, it's a physically based, spatially explicit description, right? And so the notion is that by nailing down the physical components, you should be able to get to the right answers sooner than in a regression approach. So perhaps not as much time. Nevertheless, you've got calibration in the mix of that. And so that's going to take time, and especially up against models that are based on 30, 40 years of data. And so I think we've got to be really careful about just throwing those comparisons at each other. We need to recognize that when you build a physically based model that is going to have some calibration to it, it's a taking off point. It's not a retrospective activity because you don't have the forcing data. You don't have the physical constraints necessarily for that. And so in some ways, these are apples and oranges until you get some ways down the road. And you have to start at a certain point. So there's no problem in comparing, but we have to be careful not to just assume that this is best offering versus best offering. It simply takes time to get there.
Everything's a moving target for that matter. So like what Gus presented, that stuff's a moving target now, again, with your new efforts and all that. So ours is a moving target. I know B120 is a moving target for sure, right? You guys are making updates to that. Okay, unless there's any final, it's Thirsty Thursday. These guys need to get out of here. So let me give Steven the last word back there.
All right.
And Eli, did you have something super quick? What is it?
Sure. I was just going to propose rodeo style comparisons, and that's what seems to be working for reclamation. I mean, I think there's a lot of issues with the way they implemented it. Like it pretty much excludes any model that can't run instantaneously on someone else's computer. So it excludes process-based models. But by setting up a rodeo ahead of time, you make it clear what data you're trying to hit as your target. So that solves the whole, are we using the same full natural flow data? Because those target variables to calibrate against are given to you at the start. And then it also provides predetermined error metrics where it's not in anyone's interest to decide what error metric to use next year, having already seen this year. So, I don't know a good way to necessarily implement that, but it's something that Reclamation is doing with pretty sizable cash prizes. They've gotten a lot of traction on it. And I'm just curious if it's something that like DWR or anything would ever consider.
Steven, final word.
Check. Testing. Just to make sure that I was the last one, because Caitlin told me to be the last one. FNF data, I would like to know how other people does it. Because I'm not saying it's a big can of worm, because a lot of the times rules regulations are tied to inflow, and I loathe going in there, but I would really like to know how other reservoirs does it, not so that I can learn.
Excellent.
And I think that matters a lot to everyone else, because you're calibrating the models against what we give you, and sometimes what we give you is a can of worm.
Yep. All right. Thank you, everyone. We'll see you at the base of the gondola if you're heading up the mountain tonight, and appreciate the discussion.